Imagine a single thread capable of holding the weight of a skyscraper, strong enough to ride out a storm over the ocean or to lift a drilling rig from the depths of the sea. How is this living armor born from a cold piece of steel in a world where weakness is not an option? Why does the fate of a billion-pound project hang on a microscopic flaw in a single wire? We will journey from the searing heat of the furnace and giant carousel machines to the most brutal tests of strength and endurance, where the line is drawn between what will hold and what will break. Watch to the end and you'll uncover a secret that will make you look at a simple steel cable in an entirely new light. You'll find them at work in maritime cranes, hoisting modules onto oil platforms, deep in mine shafts, erecting wind turbines in the middle of the ocean, and in the construction of monumental bridges and skyscrapers. The material used to create these immense ropes is a high-alloy carbon steel, but not just any steel. This is a grade perfected with alloys. Chromium, nickel, and sometimes molybdenum are added to the mix, each with a specific purpose. Chromium enhances corrosion resistance, while nickel adds strength and ductility. These elements transform the metal into a form of engineered armor. And to prepare this steel for weaving, it must first be drawn into wire. The initial stage is rolling. Steel billets are passed through rollers, progressively reducing their diameter. Next comes thermal quenching. The wire is heated to extreme temperatures and then rapidly cooled to create a precise molecular structure, making the steel both hard and resilient. The third step is coating. This is chosen based on the final application: a zinc coating, galvanizing, for protection against rust, or a polymer sheath for operating in aggressive environments like saltwater. But even after all this, it is not yet a finished wire. Now comes computerized calibration. Each wire is inspected by high-precision machines, measuring not only its diameter down to the micron, but also checking for microbends, tension, and symmetry. A deviation of 1/100th of a millimeter could be critical, because thousands of these wires will soon act as one. A single weak segment creates a potential point of failure. Once every wire has been treated, tested, and calibrated, one of the most spectacular stages begins: the stranding of the rope. And this isn't simply twisting wires together. It is a mathematically precise system of tension, angle, and the interplay of hundreds of individual elements. At the heart of every rope is a core, which can be steel or a synthetic fiber. It is around this core that strands of steel wire are laid in spirals. Each strand can contain dozens, even hundreds of wires, all woven in a strict, predetermined pattern. The goal is to distribute the load perfectly evenly along the entire length. Every rope has its own configuration: the angle of the lay, the number of strands. For flexibility, more thinner wires are used. For rigidity, fewer but thicker ones. The process takes place on giant stranding machines that operate like carousels. They rotate slowly, methodically, drawing individual wires from dozens of bobbins. A single machine can construct a rope over 100 meters long. As it's woven, every single wire is held at a precise tension, managed in real time by an automated system. If just one wire is twisted or over-tightened, the rope could lose its integrity. The entire operation is continuously monitored. Sensors detect the slightest vibration, and the machine will halt automatically if a fault is found. Human oversight here is minimal. Interestingly, some ropes have a composite structure, an outer layer with polymer insulation or fire-resistant coating housing internal metallic strands with different properties. When the stranding is complete, the rope is still not ready. It now faces one of its most critical trials: testing and certification. This is where it must prove it can handle the forces it was designed for. The first test is for breaking strength. The rope is secured between two colossal hydraulic grips, which then begin to pull with incredible force. We are talking about hundreds of tons of load, gradually increasing. The aim is to find the ultimate tensile strength. Ideally, the rope must withstand 3 to 5 times the load it will carry in the real world. But surviving maximum force isn't enough. It also undergoes a fatigue test, where the rope is repeatedly tensioned and relaxed, simulating thousands of real-world operational cycles. Separate tests are conducted for torsion, where the rope is twisted to assess its rotational stability. This is vital for applications where the load vector is constantly changing. Another critical phase is the environmental trials. The rope is submerged in salt water, frozen to -40 degrees Celsius or heated to over 100 degrees. Some are tested for resistance to UV radiation, chemicals, or even fire, because the conditions on a North Sea oil rig or in a mine shaft are nothing short of extreme. Only after passing this battery of tests can a rope receive certification from international bodies like Lloyd's Register or DNV. Every rope is given an individual serial number linked to its testing protocols. In some cases, its pedigree is even recorded, showing which steel mill produced the metal for every single wire. Once it has passed every trial, the rope is wound onto enormous reels, 20, 50, or even 100 meters long, and transported on special platforms. A single reel can weigh several tons. On site, the rope is installed with millimeter precision, and only after a final inspection does it begin its work in a world where there is no margin for error.
The metal hiding in every muffler. Every minute, 130 cars roll off production lines around the world, and each one hides between 2 and 7 grams of palladium, a metal more expensive than gold and platinum, so rare that all the world's reserves could fit in a single room. But without it, every modern city would choke. Palladium scrubs poisonous substances from exhaust gases. 85% of all palladium mined goes into automotive catalysts. Platinum's little brother has become the critically important metal of the 21st century. How do you extract a silvery metal worth $40,000 per kilogram from ore mined a kilometer underground in Siberia? You'll learn why palladium was named after an asteroid, how it transforms poison into harmless gas, and why its reserves could run out in 20 years. Watch until the end. The finale reveals what stands behind the clean air in our cities. This is the story of the metal the future of the automotive industry depends on. The story of palladium began in 1803 in London. British chemist William Wollaston was studying platinum ore from South America. He dissolved the ore in aqua regia, a mix of hydrochloric and nitric acids, the only solvent capable of dissolving platinum. From the solution, he extracted platinum, but noticed some impurities remained in the solution. Wollaston performed a series of chemical operations and isolated a new metal, silvery white, similar to platinum, but lighter. He named it palladium after the asteroid Pallas discovered a year earlier. Coincidence or not, Pallas in Greek mythology is the goddess of wisdom. Palladium turned out to be an amazing metal. It could absorb hydrogen in volumes 900 times its own. Picture this. A cube of palladium 1 centimeter by 1 centimeter can soak up nearly a liter of hydrogen. The metal swells up like a sponge. But the key property was discovered later: catalytic activity. Palladium speeds up chemical reactions without taking part in them. For a long time, palladium remained a laboratory curiosity. It was used in jewelry. White gold often contains palladium. In dentistry, for dental crowns. In electronics, palladium contacts don't oxidize, but consumption was minimal, just a few tons a year for the entire world. Everything changed in the 1970s when environmental regulations suddenly got much stricter. Car exhaust contains carbon monoxide, nitrogen oxides, and unburned hydrocarbons, all of them toxins. Cities were choking in smog. A solution was needed, and one was found: the catalytic converter, a device that transforms poisonous gases into harmless ones. Inside a stainless steel casing, a ceramic honeycomb structure coated with an ultra-thin layer of platinum, palladium, and rhodium. Hot exhaust gases pass through the honeycomb. On the surface of the platinum group metals, reactions occur. Carbon monoxide converts to carbon dioxide, nitrogen oxides to harmless nitrogen, hydrocarbons burn off. The converter cuts emissions by 95%. But there's a price. Each converter contains precious metals.
Palladium turned out to be perfect for the job. It's cheaper than platinum, but better at oxidizing hydrocarbons. With environmental regulations rolling out in Europe and the US, demand for palladium exploded. Production jumped from just a few tons a year to 300 tons. The price rocketed from $500 per troy ounce in the 90s to $3,000 in 2020. Palladium became more expensive than gold and platinum. Catalytic converter thefts started spreading. Thieves cut the converter out from under a car in 5 minutes and sell it for $200 to $500. The palladium inside is worth even more. The problem is, palladium is one of the rarest elements out there. In the Earth's crust, it makes up 6 parts per 10 billion. That's 30 times rarer than gold. Worldwide, only about 200 tons of palladium get mined each year. For comparison, 3,000 tons of gold, 20 million tons of copper. Palladium doesn't form its own deposits. It shows up as an impurity in nickel and platinum ores. Main sources: Russia and South Africa.
70% of the world's palladium comes from Russia, mostly from the Norilsk mining complex in Siberia. Norilsk is a city above the Arctic Circle, one of the most northern cities on the planet. Winter temperatures drop to -50. But underground lies a unique deposit of copper-nickel ores containing platinum group metals. The ore is mined in shafts up to nearly a mile deep. They blast the rock, load it onto dump trucks, bring it to the surface. The ore contains about 1% nickel, fractions of a percent copper, and just a few grams per ton of platinum group metals: platinum, palladium, rhodium, iridium. But the volumes are massive: 20 million tons of ore per year. The ore is crushed, ground into fine powder, enriched by flotation. The process is similar to lead ore enrichment. They get a concentrate containing 10 to 15% nickel and copper and elevated levels of precious metals. The concentrate is smelted in massive furnaces. This produces matte, an alloy of nickel, copper, and iron sulfides. All the platinum group metals are concentrated in the matte. Feinstein gets shipped to a metallurgical plant. There, it's converted, blasted with oxygen at temperatures hitting 1200 degrees. Iron and sulfur oxidize and get stripped away. What you're left with is crude nickel-copper alloy containing the platinum group metals. This alloy gets dissolved in sulfuric acid. Nickel and copper go into solution. Precious metals stay behind in the residue, what they call slimes. These slimes contain up to several percent platinum group metals. It's not palladium yet, but it's highly concentrated feedstock. The slimes get dissolved in aqua regia, that same acid mixture Wollaston used. All the platinum group metals go into solution. Now the ultra-precise separation chemistry begins. From the solution, they sequentially precipitate platinum, palladium, rhodium, iridium, ruthenium, osmium. Each metal precipitates at a specific pH with specific reagents. The process takes weeks. The result precipitates of various palladium salts. These salts get calcined at high temperature. You get sponge palladium, a gray porous powder. It's almost pure metal, but not yet a marketable product. Spongy palladium gets melted down in an induction furnace under argon or vacuum. Palladium can't oxidize. The molten metal pours into ingots. You end up with small bars weighing anywhere from a few ounces to 2 pounds. Silvery white with a slight steel tint. Palladium's softer than platinum, so you can roll it, forge it, draw it into wire. Palladium's melting point? 2,828 degrees Fahrenheit, lower than platinum. Density? About 0.43 pounds per cubic inch, lighter than platinum, but still a seriously heavy metal. Palladium doesn't tarnish in air, doesn't react with most acids, only dissolves in aqua regia and hot concentrated nitric acid, corrosion resistant. But here's the key property, catalytic activity. Palladium speeds up oxidation and reduction reactions. On its surface, gas molecules get adsorbed, activated, react with each other. That's exactly what makes palladium irreplaceable in automotive catalytic converters. The entire journey from ore to metal takes months and involves dozens of processing steps. How does a palladium car catalytic converter work? The device looks like a metal canister installed in the exhaust system right after the engine. Inside is a ceramic honeycomb structure, like an actual beehive. Thousands of channels in this structure. Total surface area, several square feet. The surface is coated with aluminum oxide, a thin porous layer that multiplies the area hundreds of times over. On top of that layer, palladium, platinum, and rhodium, total weight between 2 and 7 grams. Palladium and platinum oxidize carbon monoxide and hydrocarbons into carbon dioxide and water. Rhodium reduces nitrogen oxides back to nitrogen. Exhaust gases at temperatures between 750 and 1470 degrees Fahrenheit flow through the honeycomb. Reactions happen on the metal surfaces. What comes out? Almost pure nitrogen, carbon dioxide, and water vapor. Efficiency? Up to 98%. Without a catalytic converter, a car dumps dozens of grams of toxins into the atmosphere every mile. With one, fractions of a gram. A modern passenger car contains 3 to 5 grams of palladium. A truck or SUV, up to 7 grams. Here's the problem. Palladium reserves are limited and running out. There aren't many accessible deposits left. At current extraction rates, proven reserves will last 20 to 30 years. Prices are climbing. The shortage is getting worse. Automakers are hunting for alternatives to palladium. They're partially switching to platinum. It's also a catalyst, but more expensive and less effective for gasoline engines. For diesels, platinum works better. Recycling palladium from spent catalytic converters is ramping up. Old converters get collected, crushed, and the platinum group metals extracted. Recycling provides up to 30% of palladium supply. It helps, but it doesn't fully solve the problem. Demand keeps growing. Around 90 million cars roll off production lines worldwide every year. Electric vehicles don't use catalytic converters, but their share of the market is still small. Hybrids still need palladium. The palladium market's unstable. Prices swing from $2,000 to $3,000 per troy ounce. Palladium has become a strategic metal. The entire automotive industry and urban air quality depend on it. And just like that, journeying from ore a mile deep beneath the Siberian permafrost, through months of chemical operations and ultra-precise separation, palladium emerges into the world, platinum's younger brother, now the champion of clean air. A few grams of silvery metal hidden inside every muffler, saving millions of lives annually. The rarest of elements, 30 times scarcer on Earth than gold, has become critically vital to modern civilization. It's the paradox of technological progress. The more we care about ecology, the more we depend on rare metals. Every time you start your car, remember, beneath the chassis works a palladium catalyst, transforming poisons into harmless gases. A metal worth $40,000 per kilogram makes city air breathable. From the asteroid palace to automotive catalysts, 220 years of history for a metal that found its calling in the fight for ecology. But reserves are dwindling, prices are climbing, and palladium's future looks uncertain. Perhaps in 20 years, humanity will discover a replacement, or learn to recycle more efficiently, or switch to electric vehicles. But for now, palladium remains the thin silvery thread connecting a billion automobiles to clean air, the metal without which megacities would suffocate. The hidden hero of the environmental revolution, tucked away in every muffler.
Right now, 430 nuclear reactors are running on this planet. They light up cities, power factories, move aircraft carriers, but at the heart of every single one, a metal that can ignite a city or wipe it off the map: uranium. Just 1 kilogram of enriched uranium holds the energy of 2 million kilograms of coal. But how does this deadly element transform from gray ore into a gleaming fuel rod? You'll find out why miners wear dosimeters even in the shower, how centrifuges spin faster than a bullet, and what happens when a single uranium atom splits in two. Stick around to the end, because the finale shows how humanity tamed the power of the stars.
The story of uranium began long before the atomic age. In 1789, German chemist Martin Klaproth isolated a strange heavy metal from a mineral and named it after the planet Uranus, discovered just a few years earlier. Back then, nobody knew that this silvery gray element would become the most dangerous and most valuable material of the 20th century. In the 19th century, uranium was used to dye glass bright yellow and green colors. Uranium glass glowed under ultraviolet light and was considered a fashionable decoration. People didn't even suspect they were holding a potential bomb in their hands. Everything changed in 1938 when Otto Hahn and Fritz Strassmann discovered uranium nuclear fission. It turned out that a single uranium-235 atom, after absorbing a neutron, splits into 2 parts, releasing enormous energy and new neutrons. These neutrons can split the next atoms. That's how a chain reaction begins.
The world realized uranium isn't just a metal, it's the key to unprecedented power. The uranium race was on. The Manhattan Project in the US, Soviet programs, British developments, everyone was hunting for uranium deposits. And they found them. The largest uranium mines are located in Kazakhstan, Canada, Australia, and Namibia. Kazakhstan is the absolute leader, producing about 40% of the world's uranium. Canadian mines in the Athabasca Basin contain some of the richest uranium ores on the planet, up to 20% uranium versus the typical 0.2%. Australia's Olympic Dam deposit is so massive that its reserves are estimated in the millions of tons. And in Namibia, the Rossing uranium mine is one of the world's largest open-pit operations, where giant excavators work around the clock. Every year, the world mines about 53,000 tons of uranium. Sounds like a lot, but uranium is actually a rare element.
In Earth's crust, there's just 2.8 parts per million, 1,000 times less than zinc and 40 times less than lead. Uranium mining starts deep underground, or on the surface of massive open pits. Underground mines plunge down to nearly a mile deep. Eternal darkness reigns here, sliced by beams from headlamps on miners' helmets. The air is heavy, humid, saturated with the smell of explosives and dust. Temperatures hit 104 degrees. At this depth, the rock heats up from Earth's core. Miners drill holes into the uranium vein, pack in explosives, and retreat to a safe distance. The blast roars like underground thunder, and tons of rock come crashing down. Massive loaders with wheels as tall as a person scoop up the debris and haul it to the mine shafts. Uranium ore isn't pure uranium. It's rock containing just 0.1 to 20.
The rest is waste rock. But even that tiny fraction makes every stone radioactive. The dosimeters on miners' belts click constantly, measuring radiation levels. Each worker gets a strictly limited radiation dose per year. Go over the limit, you're headed home until next season. At the surface, they load the ore into dump trucks and haul it to the processing plant. That's where the first stage of turning rock into fuel begins. They crush the ore in giant mills, where steel balls the size of watermelons grind the rocks into fine dust. This dust gets mixed with sulfuric acid. Chemical leaching starts. The acid dissolves the uranium oxide, leaving the waste rock untouched. What you get is a yellow-green liquid that looks like poisonous soup. They filter it,
purify it, evaporate it, and what comes out is a bright yellow powder they call yellow cake. It's uranium concentrate, containing up to 80% uranium oxide.
Yellow cake gets packed into steel drums, 440 pounds each, and shipped to a conversion facility. But this uranium isn't reactor ready yet. The problem? Natural uranium is made of two isotopes, uranium-238, 99.3%, and uranium-235, just 0.7%. Only uranium-235 can sustain a chain reaction. So the uranium needs to be enriched, boosting the uranium-235 share to 3 to 5% for reactors, or up to 90% for weapons. At the conversion facility, yellow cake gets turned into a gas, uranium hexafluoride. This gas is poisonous, corrosive, and radioactive all at once. At room temperature, it's solid, like ice, but heat it to 133 degrees Fahrenheit and it turns straight into gas, skipping the liquid phase entirely. Uranium hexafluoride gets pumped into steel cylinders and trucked to an enrichment plant.
Here's where the most technologically complex stage begins: isotope separation. Uranium-235 and uranium-238 are chemically identical, but differ in mass by just 3 neutrons. How do you separate things that are almost the same? Gas centrifuge method. Picture a massive hall the size of a football field, packed with thousands of vertical metal tubes about 6 feet tall. These are centrifuges. Each one spins at speeds up to 100,000 revolutions per minute, faster than a speeding bullet. Uranium hexafluoride gets fed into the centrifuge, and under monstrous centrifugal force, the heavier uranium-238 gets thrown toward the walls, while the lighter uranium-235 concentrates in the center. The difference is microscopic, just 1% per pass. That's why the gas runs through thousands of centrifuges, connected in cascades. Each successive centrifuge receives slightly more enriched uranium than the one before.
The process takes months. Eventually, you get enriched uranium hexafluoride with uranium-235 content ranging from 3 to 5%. That's enough for a nuclear power plant. If you keep enriching it up to 90%, you get weapons-grade uranium. That's exactly why enrichment facilities are guarded better than fortresses. The enriched uranium hexafluoride is transported back to a facility where it's converted from gas into solid uranium oxide, a dark gray ceramic powder. This powder is pressed into small cylindrical pellets, about the size of a fingertip. Each pellet weighs around 7 grams, but contains energy equivalent to 400 kilograms of coal or 3 barrels of oil. The pellets are sintered in furnaces at temperatures of 1700 degrees Celsius. They become hard as diamond and develop a distinctive metallic luster.
Now these pellets need to be turned into fuel rods. They're loaded into long, thin tubes made from a zirconium alloy, a material that doesn't absorb neutrons and can withstand the extreme temperatures and pressures inside a reactor. Each tube is about 13 feet long and holds several hundred pellets. The tubes are hermetically sealed and assembled into bundles, fuel assemblies. A single assembly contains anywhere from 100 to 300 rods, held together in a unified structure with gaps for water circulation. One fuel assembly weighs up to 1,500 pounds. The finished fuel assemblies are shipped to nuclear power plants. Here, they're loaded into the reactor core, a massive pressurized steel vessel surrounded by walls of concrete and steel over 3 feet thick. When the rods are lowered into the reactor and the chain reaction begins, temperatures inside reach about 570 degrees Fahrenheit. Neutrons tear through the reactor core, slam into uranium-235 atoms, split them apart, and each split unleashes massive energy.
That energy heats water into steam. Steam spins turbines, turbines drive generators, and generators produce electricity that lights up millions of homes. A single fuel rod runs in the reactor for 3 to 6 years. During that time, it cranks out as much energy as an entire freight train loaded with coal or a tanker full of oil. But gradually, the uranium-235 burns out, and fission products pile up, radioactive isotopes that poison the reaction. The rod gets pulled from the reactor and dropped into a spent fuel pool, a massive tank of water 40 feet deep. Water cools the rods and absorbs the radiation. They'll sit here for years, cooling down and losing activity before they're shipped off for reprocessing or burial.
The entire journey of uranium, from a dark mine deep in the earth to a glowing reactor, is a story about how humanity learned to extract energy from the very heart of matter. From explosions in mine shafts to spinning centrifuges, from ceramic pellets to fuel assemblies, every stage demands precision, technology, and control. Uranium isn't just a metal. It's a bridge between the past, when we burned wood, and the future, when we might master nuclear fusion. Today, nuclear power provides about 10% of the world's electricity. That means every 10th light bulb on the planet shines because of uranium. But it's also a metal capable of destroying civilization in minutes. And as long as humanity holds this balance between creation and destruction, between light and darkness, we continue to exist. Uranium gave us incredible power, and now our job is not to abuse it.
Picture a metal that's everywhere in nature, yet remains one of the most expensive and difficult materials for industry to work with. That metal is titanium. It's abundant in the Earth's crust, but producing it is so labor-intensive, energy-hungry, and technologically finicky that the aviation industry literally fights for every quality pound. And that's not an exaggeration. Without titanium, there'd be no modern jet engines, no critical aircraft components, no landing gear parts, no structural elements where you need high strength, low weight, and corrosion resistance all at once. But the journey of titanium from black sand or ore concentrate to an aircraft part is remarkably far from conventional metallurgy. You can't just melt it down, reduce it with carbon, and pour it into a mold like steel or iron. Titanium is too reactive. It bonds with oxygen way too easily. It's too sensitive to contamination. And that's exactly why producing titanium for aviation isn't just mining and smelting. It's one of the most complex sequences of chemical and metallurgical operations in modern industry. In nature, titanium almost never occurs as pure metal. Industry extracts it from minerals, mainly rutile and ilmenite. Very often, these ores aren't mined in classic deep mines, but in what are called mineral sands, placer deposits that form along coastlines and in ancient sedimentary zones. This means the first stage of titanium production looks totally different from the typical picture of miners and mine shafts. Here, they might use dredges, excavators, washing systems, gravity and spiral separators that separate heavy minerals from lighter waste rock. But even after processing, what you have isn't metal yet. It's just titanium-bearing raw material. And this is where the main paradox kicks in. Titanium is extremely abundant, but extracting actual metallic titanium from its oxides is way harder than smelting many far rarer metals. That's exactly why titanium is expensive, not because it's rare in nature, but because turning ore into aviation-grade metal is brutally complex. The next stage is converting the ore into a chemical form from which pure metal can actually be extracted. For titanium, this is especially critical because the usual heat-based reduction doesn't work here. While iron or copper can be processed using relatively straightforward metallurgical methods, titanium is a different beast. Its oxide is too stable, and the metal itself, at high temperatures, binds too aggressively with oxygen, nitrogen, and carbon. So industry takes an indirect route. Titanium feedstock is first converted into titanium tetrachloride, a volatile chemical compound that can then be purified. To do this, the concentrate undergoes high-temperature chlorination in the presence of a reducing agent, and then the resulting product is sent for purification.
The key advantage of this approach is that titanium tetrachloride can be purified through distillation, removing a whole range of unwanted impurities. Essentially, this is the moment when rough mineralogy transforms into chemically controlled feedstock for the metal to come. And it's at this stage that it becomes clear. Titanium production isn't classic smelting. It's a chemical metallurgical process with extremely tight purity requirement. Once the purified titanium tetrachloride is ready, one of the industry's most critical processes kicks in, the Kroll process. This is the fundamental industrial technology that makes modern mass production of titanium for aviation, aerospace, and other high-tech fields even possible. Here's how it works. Purified titanium tetrachloride reacts with molten magnesium inside a sealed reactor. The result? The metal breaks free from chlorine and forms what's called titanium sponge. This isn't a solid ingot or finished semi-product yet. It's a porous, brittle metallic mass that looks like hardened porous rock. After the reaction, leftover magnesium and byproducts get removed. Then the sponge is sorted, crushed, and prepped for the next stage.
At first glance, you might think the sponge is almost finished metal, but really, it's only halfway through a long journey. Aviation doesn't just need titanium, it needs material with precise chemical composition, high uniformity, and predictable behavior under stress. So next, this sponge still has to be transformed into a full-fledged structural metal. The next major stage is remelting the titanium sponge into a dense, homogeneous ingot. And this is where production gets especially tricky again. Molten titanium aggressively absorbs oxygen, nitrogen, and other impurities from the surrounding environment. Even slight contamination can make the metal brittle and unsuitable for critical aircraft components. That's exactly why titanium remelting doesn't happen in a regular shop floor atmosphere. It's done in a vacuum or a controlled, inert environment. One of the key methods is vacuum arc remelting. For this process, they form a consumable electrode from titanium sponge, alloying additives, and sometimes a portion of quality scrap returns. Then, this electrode is gradually melted by an electric arc, and the metal collects drop by drop in a water-cooled mold, forming an ingot. For critically important aerospace applications, a single remelt like this often isn't enough, so the metal may go through double or even triple remelting to achieve maximum structural uniformity, stable composition, and the absolute minimum number of defects. But aviation doesn't just need pure titanium. In most cases, the foundation is special titanium alloys, and the most famous of these is Ti6Al4V, also known as Grade 5. In this material, titanium is alloyed with aluminum and vanadium to achieve a combination of properties that's practically impossible to replicate in many other metals. This alloy is noticeably lighter than steel, yet it has very high specific strength, good fatigue resistance, and outstanding corrosion resistance. That's exactly why it's used in compressor discs and blades of aircraft engines, in landing gear components, structural load-bearing elements of the aircraft, and other assemblies where every pound matters. But for titanium to become a true aerospace material, it's not enough to just melt it into an ingot. What follows is forging, rolling, heat treatment, microstructure control, and mechanical property verification. In other words, aerospace-grade titanium isn't just a metal, it's an entire series of carefully sequenced operations, each one affecting the final reliability of a part that will later operate under enormous loads. This is where it becomes clear why titanium is so expensive. First, production isn't continuous, it's largely cyclical. The Kroll process is slow and energy-intensive. It requires magnesium, chlorine, sealed reactors, and complex purification afterward.
Second, almost every hot stage demands a vacuum or inert atmosphere. Why? Because the metal reacts too aggressively with oxygen. Third, titanium itself is a nightmare to machine. It has low thermal conductivity. Heat doesn't escape into the chips. Instead, it concentrates on the cutting tool. This accelerates tool wear, slows down machining speeds, and drives up the cost of every finished part. On top of that, titanium semi-finished products require extremely precise control of structure and chemistry, and tolerances in aviation are far tighter than in mass industry. The bottom line, titanium isn't expensive because it's rare in nature. It's expensive because the entire chain, from ore to aerospace-grade alloy, is extraordinarily complex, long, and sensitive to any deviation from the process. There's one more reason titanium is so valued specifically in aviation. It fits perfectly into the philosophy of modern engineering, where weight savings directly translate into efficiency gains. A lighter aircraft burns less fuel, carries more payload, and its engine and structural components operate in more favorable conditions. But titanium isn't a universal replacement for steel or aluminum. It's used where it truly justifies its cost, in hot sections, highly stressed components, corrosive environments, and parts where the combination of strength and low weight is critical. That's why titanium production for aviation isn't just metallurgy for the sake of metal. It's an industry where every step serves a single purpose: to create a material that will perform reliably in an aircraft at high speeds, under cyclic loads, vibrations, temperature swings, and with enormous responsibility for safety. When you look at titanium's entire journey, you're witnessing a nearly perfect example of modern high-tech manufacturing. First, heavy mineral sands or ore concentrates get separated from waste rock. Then, chemical processes transform the raw material into purified, volatile compounds. Next, through the Kroll process, they obtain porous titanium sponge. After that, it's remelted into ingots under vacuum, alloyed, structurally and chemically refined several times over, and only then transformed into semi-finished products and parts for aviation. In other words, titanium's journey is a path from dirty natural mineral to a material that can work inside a jet engine or an aircraft structural assembly. And perhaps that's where titanium's real power lies. It seems like just another element in Earth's crust, but actually becomes a true engineering marvel only after incredibly complex technological processing. That's why aviation-grade titanium isn't just a metal. It's the embodiment of how far industry can push when it needs the perfect balance of strength, lightness, durability, and reliability.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread, or roving. This isn't the glass from your windows. It's a special glass fiber produced by melting glass and drawing it through microscopic holes. The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle.
This river of glass fiber now begins its journey. It passes through a system of guides and tensioners. Each of the thousands of threads must be held at exactly the same tension. If one thread sags while another is too tight, the load in the final product will be distributed unevenly, compromising its strength. The dry glass bundle is then slowly submerged in a bath filled with a thick, sticky, honey-like liquid. This is the polymer resin, the flesh that will be built upon the glass skeleton. It's a complex chemical cocktail. The base is typically a polyester, vinyl ester, or epoxy resin. To this, a hardener is added, a catalyst that will trigger a chemical reaction, turning the liquid into a solid plastic.
Various additives can also be mixed in. Pigments for color, UV inhibitors to protect the rebar from sunlight, and fire retardants. The purpose of this bath is to impregnate every single tiny fiber. The bundle must be completely saturated in the resin, leaving no dry spots. Now heavy and soaked in sticky resin, the bundle emerges from the bath and heads towards the point of its creation, the forming die. This is the heart of the entire process. Imagine a thick steel plate with the perfectly round, polished hole, its diameter precisely matching that of the future rebar. The die is heated to a specific temperature.
As the wet bundle is pulled into this hole, several things happen at once. First, the die acts like a press, squeezing out all excess resin. Second, it compacts all the glass fibers tightly together, forming a perfectly round rod. Third, the heat from the die initiates the first stage of the curing reaction. Emerging from the die, we can already see the familiar shape of a rebar, but it is still soft and vulnerable. So how does it get its famous ribbed surface? Immediately after the die, while the rod is still hot and pliable, a special glass fiber strand is wound around it. A thin resin-soaked thread is wrapped in a spiral around the surface of the rod, creating the textured pattern. The formed and wrapped rod now enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber which can stretch for dozens of meters, where a high temperature, typically around 200 degrees Celsius, is maintained. Here, the final transformation occurs. This isn't just drying. Under the heat, the resin molecules begin to rapidly link together, forming a strong, rigid, three-dimensional grid. The liquid, sticky syrup turns into an exceptionally strong and hard composite material, permanently bonding millions of glass fibers into a single, monolithic rod. As the rebar moves slowly through this hot tunnel, it acquires its final, rock-hard strength.
But what is pulling it through this long journey? At the end of the line sits a special pulling device. It typically consists of two caterpillar track mechanisms like those on a tank, positioned one above the other. They gently but very firmly grip the finished solid rebar and pull it towards them at a constant, precisely controlled speed. It is this machine that provides the force to draw the glass fibers through the resin bath, the forming die, and the oven. The speed of this movement is one of the most critical parameters controlling the quality of the final product. And so, from the other end of this long production line, an endless, perfectly straight, hard and hot GFRP rod emerges. The final act is cutting. An automatic saw is mounted across the line. It synchronizes with the speed of the moving rebar, and at the right moment, it makes a quick forward dash, and with a sharp whiz, it cuts a standard length, for example 6 or 12 meters, from the continuous rod. It then returns to its starting position. The finished, still warm rebars roll onto a cooling table, after which they are collected into bundles, tied, and sent to the warehouse. And so, before our very eyes, thousands of fragile glass threads and a barrel of sticky liquid have journeyed through baths, presses, and ovens to become the lightweight yet incredibly strong building material of the future. The market for glass fiber rebar isn't yet a giant like the steel market, but it is the boldest newcomer, rapidly gaining traction. The global market for this material is already valued in the hundreds of millions of dollars, with staggering forecasts. It's expected to grow by 10 to 12% annually. Now for the key features that are making the steel industry nervous. The first and most obvious is weight. GFRP rebar is roughly 4 times lighter than steel of the same diameter. Imagine a lorry. It can deliver 4 times more GFRP rebar in a single trip than it could steel. On the construction site, 2 workers can easily carry entire coils of GFRP rods, whereas moving steel requires a crane. This represents a colossal saving in logistics and labor. Second is strength. And here, GFRP steps into the ring and knocks steel out in the first round. Its tensile strength is approximately twice that of standard steel rebar. This means that for some structures, a smaller diameter rebar can be used, saving even more on weight and volume. But the ultimate advantage, the true superpower of GFRP, is its war on rust. The main enemy of any reinforced concrete structure, from bridges to car parks, is not the load, it's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to corrode. Rust expands in volume and literally bursts the concrete from within. And GFRP? It simply laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means the lifespan of the structure increases dramatically. A concrete structure reinforced with steel is designed for about 50 years. A structure with GFRP rebar can easily be designed for a lifespan of over 100 years.
(186 miles per hour), 60 tons of metal hurtling down the tracks faster than a race car, and it all rides on 4 wheels, each one heating up from friction to over 1800 degrees Fahrenheit at this very moment. That's hotter than red-hot iron in a blacksmith's forge. One micro crack just 0.08 of an inch wide, and you've got a catastrophe at 186 miles per hour. How did they build wheels that can withstand this hell? What kind of steel doesn't crumble under repeated heating cycles? Why can't the metal contain more than 2 parts hydrogen per million? You'll discover how the world's strongest wheels are born, what brutal tests they endure, and why defects here are simply impossible. Stick around till the end. The finale reveals what's behind every second of safe travel at 186 miles per hour. The story of high-speed rail began in 1964 when Japan launched the legendary Shinkansen train. A speed of 130 miles per hour was revolutionary, but conventional wheels couldn't handle that kind of stress. The metal would crack, the surface would fail from overheating. Engineers faced a problem. At 185 miles per hour, a wheel heats up from friction against the rail to over 1800 degrees Fahrenheit. That's a temperature where ordinary steel loses its strength and starts to deform. Every braking, a thermal shock. Every acceleration, a new cycle of heating and cooling. The metal fatigues. Microcracks form. And remember, each pair of wheels carries tens of tons, an entire car weighing around 50 to 60 tons. They needed fundamentally new steel and a completely new manufacturing process. Metallurgists developed a special alloy capable of withstanding the extreme operating conditions of a high-speed wheel. This isn't just steel. It's a precision material with strict requirements for every element. Harmful impurities are reduced to the absolute minimum. Hydrogen gets special attention. This tiny atom can penetrate steel's crystalline lattice and make it brittle. That's why hydrogen content can't exceed 2 parts per million. 2 parts per million, that's like 2 grains of sand in a ton of metal. Only special steelmaking furnaces with vacuum degassing can achieve this purity. Molten steel is held under vacuum so hydrogen leaves the metal. Dozens of sensors monitor every heat. The slightest deviation and the entire batch gets remelted. There are no compromises here. Once the steel is ready, the really impressive part begins. Multi-stage forging of the wheel center. A massive ingot of red-hot metal weighing several tons is fed under a giant hammer. First strike, and the metal starts taking shape. The blank's temperature? Around 2,200 degrees Fahrenheit. The metal glows bright orange, radiating unbearable heat. A forging hammer weighing hundreds of tons slams down on the workpiece with enough force to crush its tank. But here, everything's precise. Every strike calculated by computer. The metal flows, taking the desired shape, while its internal structure densifies. Forging isn't just about shaping, it's about forming the right crystalline structure that'll deliver strength and toughness. After each strike, they rotate the blank, reheat it, hit it again. The process goes on for hours. After forging, the wheel center looks like a rough blank. It's still far from the final wheel, but the metal has already gained internal strength. Now begins the heat treatment, quenching. The wheel is heated to a critical temperature of around 1,600 degrees Fahrenheit and held until the entire structure becomes uniform. Then, rapid cooling in oil or water. The metal freezes in a special state, hard but still too brittle. That's why the next stage is tempering. The wheel is heated again, but to a lower temperature around 900 degrees Fahrenheit and slowly cooled. The metal becomes elastic, tough, capable of absorbing impacts without cracking. It's this combination of hardness and toughness that allows the wheel to withstand hellish working conditions. Heat treatment takes several days, there's no rushing this. Now the wheel heads to machining. Powerful lathes cut away excess metal, shaping perfect geometry. A high-speed train wheel must be perfectly round, accurate to hundredths of a millimeter. The slightest asymmetry? At nearly 200 miles per hour, vibration kicks in. It'll destroy the wheel, the rail, and the car's bearings. The lathe tool peels away metal, layer by layer, revealing a gleaming surface. It's hypnotic. The massive wheel spins, the cutting tool traces the circumference, and long steel shavings curl into spirals before dropping down. Special sensors constantly measure diameter, checking for deviations. After turning, the wheel gets polished to a mirror finish. But the most critical step? Still ahead: quality control. Every wheel goes through a battery of brutal tests. First up, ultrasonic inspection. Ultrasonic waves pass through the metal. If there's even a micropore, void, or crack, just 0.008 of an inch in size, the wave bounces back, and the sensor catches it. A defect that small can become a failure point at high speed. A wheel with that defect? Rejected immediately, no exceptions. Next, magnetic particle inspection. The wheel gets magnetized and dusted with metal powder. If there's a surface crack invisible to the naked eye, the magnetic field distorts at that spot, and the powder gathers into a line. Shows the exact location of the defect. These methods catch flaws you couldn't spot without specialized equipment. But for a high-speed wheel, finding a defect isn't enough. There shouldn't be one at all. After non-destructive testing, samples from each batch are sent for destructive testing. Metal specimens are cut from the wheel and subjected to brutal loads. The specimen is stretched until it breaks to determine ultimate tensile strength. They hammer it at -40 degrees Fahrenheit to test cold toughness. They heat it to 1800 degrees and rapidly cool it hundreds of times in a row, simulating braking and acceleration cycles. If the metal fails even one test, the entire batch is rejected. No compromises. Meanwhile, the wheel is weighed to the nearest gram, balance is measured. If the center of gravity is off by even a fraction of an inch, the wheel is unbalanced and can't be used at high speed. Only wheels that are perfect by every measure get cleared for installation on high-speed trains. Once a wheel passes all inspections, it gets stamped with a special code. This code contains everything: the steel batch number, forging date, craftsman's name, results of every test. If 10 years down the line someone spots even the tiniest defect on that wheel, the code lets them trace back the entire production history and pinpoint the cause. Wheels get mounted on axles in pairs. Each pair has to match perfectly in weight and dimensions. Then the axle with its wheels gets installed into the railcar bogie. The bogie is an incredibly complex piece of machinery with bearings, shock absorbers, and a braking system. And it's the wheels that bear the brunt of it all. Each pair of wheels carries around 15 to 20 tons of railcar weight, plus dynamic loads from acceleration, braking, and taking curves. At speeds of nearly 200 miles per hour, those impact forces multiply several times over. A high-speed train wheel lasts about 600,000 miles. That's circling the Earth at the equator roughly 25 times. During that lifespan, the wheel endures tens of thousands of heating and cooling cycles, millions of impacts against rail joints, constant friction with forces measuring in tons. Every few months, wheels are removed and inspected. They measure the rim thickness, search for cracks, check for wear. If the thickness has decreased beyond acceptable limits, the wheel gets scrapped. If there are signs of metal fatigue, scrapped. Passenger safety doesn't allow for compromise. Only a handful of factories worldwide can produce these wheels. Japan, Germany, France, China, the leaders in this field. Each factory guards its technological secrets, its unique steel composition, its heat treatment methods. This is the highest level of metallurgy and engineering. And just like that, journeying from molten steel through the hellfire of forging, through ultrasonic and magnetic trials, through inspection of every single millimeter, a wheel is born into this world, one capable of carrying 60 tons at speeds of nearly 200 miles per hour. This is a story about how humanity learned to tame force and velocity. Each wheel is a symphony of engineering genius, metallurgical artistry, and ruthless quality control. Contained within it, thousands of hours of labor from hundreds of specialists, dozens of technological operations, and absolute zero tolerance for defects. When you board a high-speed train and landscapes blur past your window at nearly 200 miles per hour, remember this. Beneath you sit 4 wheels, each one having passed through hell itself, all so you can reach your destination safely. This isn't just metal. This is your life guarantee at breakneck speed.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart? A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you.
Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum, at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures. The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation.
In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt. That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder. In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture.
Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder. The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter. All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast. To turn a bare base into waterproofing material, the roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness.
The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance. After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes one side is left with a strip without granules, covered with pure bitumen.
When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat.
Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Roofu Felt new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and minus 22 degrees of cold, serving for decades without a single crack.
Somewhere in the world right now, a concrete giant is being born, capable of spanning a space as wide as an entire basketball court, and all of this without a single support. How can a lightweight hollow slab withstand the weight of hundreds of tons? Why do builders say that within these slabs lies the power of steel muscles? And most importantly, what secret makes them so unique that annually in North America, over 17.5 million square meters of these structures are produced, the area of 30 pentagons? Stay until the end, and you'll discover the secret that will forever change your understanding of concrete. The slip former machine crawls along a 590-foot forming bed at approximately 4 feet per minute. Doesn't sound terribly fast? Now let's do the maths. That's 200 feet per hour. That's nearly the length of an Olympic swimming pool, born from concrete in less than an hour. During a single 10-hour shift, one such bed can churn out almost half a mile of perfectly formed concrete slab. Now for the main feature, the voids. These holes inside aren't simply for aesthetics. They reduce the slab's weight by nearly 50% compared to a solid slab of the same thickness. Imagine constructing an office center with a floor area of 100,000 square feet. If the floors were made from ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just removed 2,000 tons of excess weight from the building. That's the weight of roughly 500 adult elephants, which foundations and columns no longer need to support. This allows the entire building structure to be made lighter, more elegant, and most importantly, considerably cheaper. But how can such a lightweight slab be strong? The secret lies in those tension steel muscles. The concrete used in these slabs isn't what you have on your pavement. This is high-strength concrete, withstanding pressure exceeding 8,000 pounds per square inch, whilst ordinary concrete manages only 3,000 or 4,000. And the steel cables inside are tensioned with such force that they create constant compression within the slab. That's precisely why these slabs are adored for constructing car parks, supermarkets, and open-plan offices. Annually in North America, over 17.5 million square meters of hollow core floor slabs are produced. This figure simply doesn't fit in one's head. It's an area sufficient to construct 30 buildings as gigantic as the Pentagon. Every year. This isn't merely a building material, it's an entire industry built on speed, efficiency, and intelligent use of resources. Everything begins not in a concrete mixer, but on a gigantic, perfectly flat aerodrome inside the workshop. This is the forming bed. Imagine a perfectly level, polished steel runway several feet wide, but in length 400, 500, and sometimes 600 feet. Beneath this runway lie pipes through which hot water or steam circulates to keep it warm. At both ends of this runway stand massive steel anchors embedded in thick concrete foundations. Between these two anchors, high-strength steel cables or strands are tensioned. This isn't ordinary wire. It's several steel threads woven together, each capable of supporting the weight of a motor car. They're laid along the entire length of the 590-foot bed, forming the future skeleton of the slab. One end of each cable is securely fixed in the anchor. To the other end is connected a gigantic hydraulic jack, and this jack begins to pull. It tensions each of these steel cables with a force of 30 or 40,000 pounds. The steel muscles tense up, becoming as hard as the strings of a gigantic guitar and store colossal energy within themselves.
This is secret number 1, pre-stressing. When the steel skeleton is tensioned, the main character enters the stage, the forming machine or slip former. This is one of the most astonishing machines in the construction world. Imagine a strange, squat, self-propelled creature that slowly crawls along rails beside our long bed. At the top, it has a large hopper into which concrete is poured. But this isn't ordinary liquid concrete. This is so-called zero-slump concrete. It's so dry that it resembles damp earth. And so this machine begins its slow journey. Secondly, special vibrators and compactors with incredible force tamp this dry mixture, making it extraordinarily dense. And thirdly, most importantly, inside the machine are special forming tubes that, whilst vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth voids. The machine, like a gigantic concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab. Because the concrete is so dry, it instantly holds its shape and doesn't spread. This is secret number 2, voids that make the slab 50% lighter than a solid one. When the machine reaches the end of the 590-foot bed, its work is complete. But our slab is still green and weak. The time arrives for a spa treatment. Workers cover the entire length of this concrete ribbon with enormous insulating tarpaulins. Hot steam is fed beneath these tarpaulins. This creates a sauna effect that dramatically accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength. But in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened, the moment of release arrives. Workers slowly release the tension on the hydraulic jacks. Now it's not simply concrete, it's pre-stressed or compressed. This means that when a load acts upon it from above, attempting to bend it, it must first overcome this built-in compression force. This is precisely what allows it to span enormous distances without additional supports. And the final act of this performance? Cutting. Along rails beside our long concrete ribbon travels a gigantic saw. This is a monster with an enormous disc covered in industrial diamonds. With a deafening roar and fountain of sparks and water, this saw cuts the slab with incredible precision into pieces of the required length. Ready, perfectly level, lightweight, and incredibly strong slabs are lifted by gigantic cranes and loaded onto lorries.
There's a metal so rare that humanity mines less of it in an entire year than it does gold in a single day. A metal that costs anywhere from $4,000 to $9,000 per kilogram. A metal you've probably never heard of, yet right now, it's keeping the plane you flew on for vacation from falling out of the sky. This is rhenium, the rarest stable element in Earth's crust. A silvery white metal that doesn't exist as a standalone ore and is only extracted as a byproduct. Without it, there would be no modern jet engines, and aviation would be stuck at mid-20th century levels. Let's start with the scale of rarity. Rhenium makes up about 7/1,000ths of a part per million in the Earth's crust. For comparison, gold is 4/1,000ths, platinum is 5/1,000ths. The numbers seem comparable, but there's a fundamental difference. Gold and platinum can be found as nuggets or concentrated ores. Nature sometimes gathers them in one place. Rhenium is never found that way. It's scattered as microscopic impurities in other ores, mainly molybdenum and copper. The concentration is so low that even calling it rhenium ore is incorrect. It's always ore of something else that happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's more often used as alloys or powder. In nature, rhenium occurs in just one mineral, jacasganite, which is so rare it literally exists in only a few places on the planet and has no industrial significance. All industrial rhenium comes as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. A byproduct of a byproduct. That's what rhenium is. Think about the scale here. To get just 1 kilogram of rhenium, you need to process roughly 200,000 tons of copper ore. 200,000 tons of rock for a single kilogram of metal. It's like searching for a needle, not in a haystack, but in an entire field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the US, Kazakhstan, and Armenia. Chile dominates, about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where they extract copper and molybdenum, pulling out rhenium along the way. The pit is so massive you can see it from space, roughly 2 3/4 miles long, nearly 2 miles wide, and over 3,000 feet deep. Extracting rhenium is complex and multi-staged. First, copper ore gets mined and enriched through flotation to produce copper concentrate. That concentrate contains molybdenum, which also gets enriched and separated out. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically 0.05 to 0.2%. Sounds convoluted, but it's essentially a chain. Copper ore to molybdenum concentrate to rhenium solution. At each stage, volume drops by factors of thousands, while value skyrockets. The molybdenum concentrate gets roasted in special furnaces at around 1,100 degrees Fahrenheit and higher in open air. Molybdenum oxidizes to trioxide, which can then be reduced back to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which vaporizes at this temperature and escapes with the gases. Those gases pass through a complex system of scrubbers, towers where they're washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or perinates. Rhenium concentration in these solutions is tiny, grams per liter, but that's something you can work with. The solution is purified of molybdenum, copper, lead, and other metal impurities through multi-stage chemical treatment, extraction, ion exchange, precipitation. Then rhenium is precipitated as a white crystalline powder, ammonium perrhenate. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen at temperatures exceeding 1,800 degrees Fahrenheit. Hydrogen reduces the rhenium oxide to pure metal. The result is rhenium powder, which can then be sintered, melted, or used directly in alloy production. Each year, humanity produces about 50 tons of rhenium. 50 tons! That's the entire global output. For comparison, about 3,000 tons of gold are mined annually. Copper, 20 million tons. Rhenium is so rare that global reserves at any given moment are measured in hundreds of tons, not thousands or millions. Here's the question: why mine something this rare in the first place? The answer? Jet engines. About 80% of all rhenium goes to the aviation industry for making superalloys that form turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 2,700 degrees Fahrenheit. That's above the melting point of the alloy the blade is made from, so it's cooled from the inside by airflow through microchannels. The pressure is colossal. The blade spins at tens of thousands of revolutions per minute, experiencing monstrous centrifugal loads. A corrosive environment with sulfur impurities from jet fuel. And all of this for years of continuous operation with zero margin for error. Because if a blade cracks mid-flight, the engine destroys itself. Nickel-based superalloys, the primary material for blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, titanium. But even these incredibly complex alloys couldn't withstand high temperatures for extended periods, until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of a superalloy and blocks defect movement in the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load when heated. All metals creep, but rhenium slows this process down dramatically. Adding just 3% rhenium to a nickel superalloy raises the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much, but in jet engines, every 18 degrees of additional temperature yields roughly 1% more efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. A single turbine blade can hold anywhere from 5 to 20 grams of rhenium. One engine on a large passenger jet, about 13 pounds of rhenium in the blades alone. 13 pounds of metal worth up to $50,000 in a single engine. And a plane has 2 engines. Every year, thousands of jet engines are manufactured. Passenger, cargo, military, and virtually all the rhenium mined goes straight into them. Because of its rarity and high cost, the industry is desperately trying to reduce rhenium consumption. New generations of superalloys with lower content are being developed, along with the use of ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive, so for now, it's just research. Single crystal blade technology makes rhenium work smarter. Instead of a regular polycrystalline structure, each blade is grown as one massive crystal with no grain boundaries, which are weak spots at high temperatures. This lets you cut down on rhenium content while keeping performance. But the process is complex and expensive. Each blade is grown individually in specialized vacuum furnaces with extremely slow, controlled cooling that takes hours. Recycling rhenium from spent blades is mission-critical. After thousands of hours in hellish conditions, blades wear out and get replaced. The old ones don't get tossed, they're melted down, rhenium and other precious metals extracted, and used again. Around 30% of rhenium comes from recycling, more than most other metals. And the reason's simple. At these prices, nobody can afford to throw rhenium away. The remaining 20% of rhenium is used in other areas. Platinum rhenium catalysts in oil refining to boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. The strategic importance of rhenium is enormous. Countries without access to rhenium cannot produce modern jet engines. And this isn't just a matter of civil aviation, but military, fighters, bombers, cruise missiles. Interestingly, rhenium was one of the last stable elements to be discovered. German chemists found it in 1925 while examining platinum ore through spectral analysis. They named it after the Rhine. Before that, Mendeleev had predicted the existence of element number 75, but no one could find it because of its extreme rarity. Basically, the entire world's supply of this metal would fit in a few trucks, and the whole world's aviation depends on those few trucks.
Steel cables were invented to replace ropes made from natural fibers. Ropes couldn't handle heavy loads. Chains were stronger but 10 times heavier. Steel cables solved both problems. Today, these cables hold up bridges, lift cranes, anchor oil platforms at depths of over half a mile, diameter up to 21 inches, weight 70 tons. Breaking strength, 9,700 tons. That's the weight of 50,000 cars. How do you make a cable that won't break? Today, you'll see the complete process, from a steel rod just a fifth of an inch in diameter to a giant cable 900 feet long. If you want to see how thin wire transforms into a monster with a 10,000-ton breaking strength, subscribe to the channel. Here we show you the industries that hold the world together. History. The modern steel cable was invented in 1834 by German engineer Wilhelm Albert. He developed it for coal mines. Hemp and manila grass ropes couldn't handle the job. The weight of coal in a cage? Over 3,000 pounds. Mine depth? Nearly 1,000 feet. Hemp rope broke from moisture and rubbing against shaft walls. Albert braided cable from steel wire. Wire diameter, just under 1/10 of an inch. 6 wires per strand. 6 strands around a core. Cable diameter, 3/4 of an inch. Strength, 5 times stronger than hemp. Lasted years instead of months. During the World War, steel cables anchored mines to the ocean floor. Deployment depth, up to 300 feet. Water pressure, 150 pounds per square inch. A cable just over an inch thick held a 600-pound mine, plus current and waves. Today, steel cables are everywhere. Cranes, elevators, suspension bridges, drilling rigs, ski lifts. Wire drawing, it all starts with rod, a steel wire 5.5 millimeters in diameter. The rod is made from grade 70 to 80 steel. Carbon content, 0.7 to 0.8%. Manganese, 0.6%. This is high carbon steel, hard and strong. The rod unwinds from a coil weighing 2 tons. It's pulled through a drawing mill. This is a series of dies with holes of decreasing diameter. First die, diameter 4.8 millimeters. Second, 4.4. Third, 4.0. Fourth, 3.6. Fifth, 3.2. Sixth, 2.8. Seventh, 2.4. Eighth, 2 millimeters. 8 passes total. Each pass reduces the diameter by 10 to 15%. Between the dies are pulling drums. Drum diameter, 500 millimeters. Rotation speed, 300 revolutions per minute. Linear drawing speed, 470 meters per minute. That's 28 kilometers per hour. The wire heats up from friction. Temperature exiting the die, 200 degrees Celsius. Cooled with water. After drawing, the wire is hard. Tensile strength, 1800 megapascals. Elongation, 2%. It's brittle. Heat treatment needed. Heat treatment. Heat treatment. The wire gets heated in a furnace to 1650 degrees Fahrenheit. Hold it there for 20 minutes. The steel structure reorganizes. Carbon dissolves into the lattice. Then it cools in air at a rate of 180 degrees per hour. Slow cooling. You get tempered steel. Hardness drops, but ductility increases. Elongation, 8%. The wire's now flexible. Ready for rope making. Strand twisting. Take 6 wires, diameter 0.08 inches. Twist them around a central 7th wire. Lay length, 4 3/4 inches. That's the distance one wire takes to complete one full wrap around the center. Helix angle, 15 degrees to the axis. Twist direction, right hand. Looking along the strand, the wires spiral clockwise. You get a strand, diameter 0.24 inches. Starting wire length, 3,300 feet. Finished strand length, 3,100 feet. The difference, that's what the twisting eats up. The strand bends easy. Bend radius, 6 inches. Strand strength, 70% of the combined wire strength. Losses from bending and friction. Rope stranding. 6 strands, 1/4 inch in diameter, twisted around a core. The core is organic. A hemp rope, 1/4 inch diameter. It's soaked in lubricant. Hemp is elastic. It absorbs shock loads. Stores lubricant inside the rope. There can be more strands. Standard construction is 6 by 7. 6 strands with 7 wires each. There are 18 by 7 ropes. 18 strands, 7 wires per strand. There's 36 by 7. More wires mean a more flexible rope. The diameter of a 6 by 7 rope with core quarter-inch wires is about 3/4 of an inch. Breaking strength is 50 kilonewtons. That's 5 tons. Weight is about half a pound per foot. The rope gets wound onto a drum 6.5 feet across, 5 kilometers per drum. That's over 3 miles. Weight of the drum with rope is 8 tons. The ropes ship out to plants that make giant cables. Manufacturing giant ropes. United Offshore Services in the Netherlands makes ropes ranging from 4 3/4 inches to 21 inches in diameter. The factory houses a machine that's over 650 feet long. It twists finished ropes around a central core rope. Here's an example. They're making a rope that's 13 inches in diameter. They take 6 ropes, each about 4 inches thick, plus a central rope that's 4 3/4 inches. Then they twist them together. The rope spools get mounted on a rotating carousel. The carousel is nearly 40 feet across. It spins at 2 revolutions per minute. The ropes unwind from the spools. They pass through guide rollers. They twist around the central rope. The lay length is 71 inches. The lay angle is 20 degrees. Twisting speed is 11.5 feet per minute. In 1 hour, they produce 690 feet of rope. The finished 13-inch rope gets wound onto a spool that's 13 feet in diameter. Breaking strength? 9,700 tons. That means this rope won't snap until you load it with 9,700 tons. Marking and lubrication. The cable gets marked along its entire length with different colored paints. Red section, the start. Yellow, the middle. Blue, the end. Every 33 feet, a marker with a number. Then they lubricate it. They use lithium-based grease. Drop point temperature 356 degrees Fahrenheit. The grease protects against corrosion and reduces friction between the wires. The cable runs through a bath of liquid grease heated to 176 degrees. The grease soaks into the core and between the strands. Then they apply an outer layer, anti-corrosion coating. It's a thick paste made from paraffin and corrosion inhibitors. Coating thickness, 0.02 inches. The final cable, length 558 feet, diameter 13 inches, weight 76 tons, breaking strength 10,700 tons. They move it with a crane rated for 165 tons. One end gets hooked. They lift. The cable hangs vertically. Lift height, 164 feet. You need a tower. At the factory, there's a tower 197 feet tall, specifically for this. Super long ropes. Hendrik Vader Group in the Netherlands makes the longest ropes in the world. Length, 920 feet. Diameter, 16 inches. Different technology. The machine travels along rails 1,000 feet long. At the start sit spools of rope. 8 spools. On each, a rope diameter 10 inches, length 920 feet, weight 110,000 pounds. Strength of each, 7,700,000 pounds. The machine starts moving. Speed, 6.5 feet per minute. The ropes unspool. They twist around a central rope diameter 10.25 inches. Lay length, 6.5 feet. The machine travels 1,000 feet in 2.5 hours. You get a rope diameter 16 inches, length 920 feet, weight 440,000 pounds. Strength, 31 million pounds. That's the weight of 80 tanks. At the end, they make a loop. They bend the rope back 15 feet. They splice the free end with the main rope. You get a loop 15 feet long. Loop diameter, 5 feet. The splice is locked with steel clamps. 10 clamps. Each clamp, 2 steel half cylinders. Tightened with 8 M36 bolts. Torque, 590 foot-pounds. Transport and deployment. A rope 900 feet long, weighing 440,000 pounds, lies coiled on the factory floor like a snake. It needs to be loaded onto a ship. They use 3 forklifts, each rated for 55,000 pounds. They lift the rope at 3 points. Drive it to the dock. Distance 1,600 feet. Speed, half a mile per hour. Time, 30 minutes. At the dock stands a crane rated for 880,000 pounds. It grabs the rope by its loop, lifts it, lowers it into the ship's hold. The ship carries the rope to Norway, to the Åsgard oil and gas field in the North Sea. Sea depth, 980 feet. A floating production platform sits there. Platform weight, 110 million pounds. The platform is held by 8 anchors. One rope 16 inches in diameter runs to each anchor. Each anchor weighs 440,000 pounds. Sits on the seabed. The rope runs from the anchor to the platform. Rope tension, 2 million pounds in calm weather. In a storm, 6.5 million pounds. Safety factor, 5 times. The rope is rated for 20 years of service. Inspected every 3 months. They send down an underwater vehicle with a camera. Inspect every foot. Looking for broken wires, corrosion, wear. If wear exceeds 10%, they replace the rope. Every year, hundreds of oil platforms get installed in the world's oceans. Each one weighs tens of thousands of tons, and at some point, all that weight hangs from a single hook. Not a cable, not a beam, but a hook. A piece of forged steel that looks like a giant fishing hook from another dimension. Around it, the North Sea, a storm, 30-foot waves, a crane swaying on the deck of a ship, and the hook holds. It holds 8,000 tons. That's roughly the weight of 8,000 cars lifted simultaneously above the water's surface. One invisible microcrack half a millimeter wide, and a structure worth billions of euros plunges to the bottom, along with everything attached to it. How do you forge a monster capable of holding 10,000 tons in the middle of a raging ocean from molten steel, at temperatures exceeding 4,000 degrees Fahrenheit? And what critical moment do manufacturers carefully hide from prying eyes? Watch until the end. The answer will surprise you. It all starts with choosing the metal. For giant crane hooks, they use special structural steel where the carbon content doesn't exceed 1%, while chromium additives up to 2% and molybdenum up to 0.5% deliver tensile strength exceeding 145,000 pounds per square inch. These elements aren't chosen randomly. Chromium provides corrosion resistance for marine conditions, and molybdenum prevents brittleness at low temperatures because a hook might operate in the North Sea, where in winter the water barely stays above freezing and the air gets even colder. The raw material arrives as briquettes or ingots weighing 44,000 pounds each. They're loaded into powerful electric arc furnaces with a 440,000 pound capacity. Giant vessels 30 feet tall with graphite electrodes 24 inches in diameter. Steel for these hooks comes primarily from Scandinavia, where it's melted in vacuum furnaces with special composition control at every stage. The logistics are impressive even before production begins. 44,000-pound ingots arrive by barge right to the factory docks. If you're curious how things are made that human lives depend on in the open ocean, subscribe to the channel right now and hit that bell so you don't miss the next episode. When a current of up to 100,000 amps flows between the electrodes and the metal, it creates an arc about 20 inches long that heats the furnace contents to over 3,600 degrees Fahrenheit. This isn't just hot, this is the temperature where steel stops being a solid and transforms into glowing liquid. The furnace slowly rotates for even mixing, while gases are drawn off through powerful filters. The melting process takes 4 to 5 hours, during which the metal is purified through vacuum evaporation and argon purging. The finished melt, a bright yellow color, is poured into ladles lined with fire brick. The temperature at discharge, around 3,000 degrees Fahrenheit. Cranes lift the ladle and transport it to the casting line, where prepared molds are already standing. Massive steel structures weighing up to 200 tons each. The mold geometry is calculated accounting for 2% metal shrinkage. If you don't build in this allowance, the finished blank will come out smaller than required. They pour at a 45-degree angle to avoid air pockets. A stream of liquid metal about 20 inches wide fills the mold in 10 to 15 minutes. Then they seal it with a lid and move it into a controlled cooling zone. And this is where one of the most critical stages of the entire process begins. For the first 24 hours, the temperature drops only to around 1,500 degrees Fahrenheit. The next 2 days, down to 400 degrees. Full cooling to room temperature takes up to a week. Sensors continuously monitor temperature gradients at a depth of 4 inches. The slightest variation can cause thermal stresses that lead to internal cracks, invisible from the outside. During cooling, the metal crystallizes, forming a coarse structure that's later optimized through heat treatment. Workers in protective suits monitor the process through viewing panels, while automated systems record thousands of parameters every minute. The finished blank weighs between 100 and 200 tons, stretches up to 40 feet long, and measures up to 6.5 feet in diameter at the base. Once the lengthy cooling period is complete, the workpiece is pulled from the mold, using cranes rated for 300 tons and transported to the forging shop, a massive facility covering 22,000 square feet with ceilings 80 feet high. Here stand hydraulic presses capable of exerting up to 50,000 tons of force. That's not a typo. 50,000 tons of pressure on a single point. For comparison, the Eiffel Tower weighs about 7,000 tons. These presses push 7 times harder. The workpiece is cut into sections 20 to 26 feet long and reheated in gas furnaces to 2,200 degrees Fahrenheit. The metal glows bright red and becomes malleable. Workers in heat suits use magnetic grips to position a section under the press. First stage, rough deformation. The press descends with up to 10,000 tons of force, compressing the metal by 20 to 30% in a single cycle. Each strike lasts seconds, gradually transforming the cylindrical blank into the recognizable silhouette of a hook. Next comes intermediate forging. The metal gets stretched out, they shape cable holes up to 2 feet across and lugs 6 inches thick. The presses are equipped with complex dies made from high-strength steel, matching the exact geometry of the future hook. Total forging cycles, up to 50 per section, with breaks for reheating every 10 to 50 minutes. Between press strikes, they constantly flip and reposition the workpiece. This ensures even densification of the metal throughout the entire volume. Forging doesn't just shape it. It improves the internal structure of the metal, refining the crystalline grain and multiplying the strength compared to the cast state. The final forging stage, precision work on the working section. The main arc of the hook reaches over 3 feet in diameter, wall thickness, 12 inches, bend radius, 8 feet. The press dies work with accuracy down to a fraction of an inch, forming reinforcement ribs and flanges. After each strike, they blow off the scale with compressed air at 90 pounds per square inch. After forging comes heat treatment, a stage without which the hook would be just a pretty but unreliable hunk of metal. The piece is placed in a furnace for tempering at 1200 degrees Fahrenheit for 20 hours. This relieves the internal stresses built up during forging and gives the metal the necessary impact toughness. Then comes machining on milling equipment. Surfaces are ground to specified roughness. Mounting holes are drilled. Threads are cut into the attachment points. Each hook weighs between 50 and 150 tons depending on load capacity. Manufacturing takes anywhere from 3 to 6 months. The plant produces up to 20 of these units per year, and each one costs millions of euros. They go to crane companies that install oil platforms in the North Sea, the Persian Gulf, and off the coast of West Africa. Now here's where it gets really interesting: ultrasonic testing. This is where manufacturers hide a detail they'd rather not talk about. Every hook gets checked for hidden cracks. Sensors scan the metal with a 5 MHz wave, detecting defects as small as half a millimeter. If even one microcrack shows up, the part gets scrapped. No negotiations, no exceptions. Why is this so critical? Because these hooks work in conditions where failure isn't an option. An offshore crane lifts a platform section weighing 8 to 10,000 tons to a height of 100 to 130 feet above sea level. Waves slam the vessel's hull, the crane sways, the load cycles constantly, slackening slightly, then building again. These cyclic loads are especially dangerous. They make cracks grow even when the overall stress stays within design limits. Under these conditions, a microcrack that slipped past inspection turns into catastrophic failure within weeks. That's why every hook gets tested not once but multiple times. Ultrasound, X-ray, magnetic particle inspection, load tests up to 120% of rated capacity. After passing all inspections, the hook's surface is coated with an epoxy layer 200 microns thick to protect against saltwater corrosion. Then they apply the markings: serial number, steel grade, manufacturing date, and load capacity. This is the hook's passport, which will follow it throughout its entire service life. The global fleet of offshore cranes exceeds 4,000 units, of which around 1,200 are floating vessels with lifting capacities above 5,000 tons. Hook production for them is concentrated in Europe, primarily in the Netherlands, Norway, and Germany, and SN total output across the entire industry comes to just a handful of units per year. The finished hook is loaded onto a specialized platform and shipped to the vessel. There, in the open ocean, they'll attach a cable to it, hook a platform section to that cable, and this piece of forged steel, born from molten scrap, will single-handedly hold the weight of several hundred railroad cars. Waves, wind, rolling seas, and it holds. Because every press strike, every hour in the furnace, and every pass of the ultrasonic probe were done with zero margin for error. Every knife in your kitchen, every spoon in your drawer, every sink, every pot, every bolt in a skyscraper. All of it exists because of one gray-green rock lying hundreds of feet underground: nickel ore. Without it, stainless steel wouldn't exist at all. Nickel is what transforms ordinary iron into metal that won't rust for decades. Add 8% nickel to steel, and it withstands seawater, acids, extreme temperatures. Every year, humanity mines 3 million tons of this metal. Value: $50 billion. But the journey from rock in the ground to shiny stainless steel sheet? It's technological hell. Explosions in quarries. Smelting at 2,700 degrees Fahrenheit. Chemical baths with sulfuric acid. Electrolysis under thousands of volts. How do you get metal that's 99.9% pure from gray rock that looks like an ordinary stone? Watch till the end. You'll see how the foundation of modern civilization is born. Planet Earth holds 300 million tons of nickel, but it's buried deep, The biggest deposits are in Indonesia, the Philippines, Russia, Canada, Australia, China, and the US. Not miners, processors and consumers. America uses it for aerospace and nuclear reactors, but it all starts in the pits. Open pit mines in Indonesia are wounds in the jungle the size of a city. A pit 1,000 feet deep, 3 miles wide. Excavators with 700 cubic foot buckets gnaw at the earth around the clock. The ore here is called laterite. It's a reddish-brown rock that looks like clay. Just 1 to 2% nickel. The rest? Iron, silicon, magnesium. But even these scraps of nickel make mining profitable. One Belazi haul truck carries 300 tons of ore out of the pit. 500 trips like that a day. 150,000 tons of rock daily. That's an entire mountain of material you need to squeeze metal from. The ore heads to primary processing. Here it's crushed and sorted. Massive jaw crushers grind car-sized chunks down to 4-inch pieces. The noise is so intense workers wear noise-canceling headphones. Then cone crushers pulverize the rock to gravel size. Mills with hardened steel balls turn the gravel into powder. Inside a 65-foot rotating drum, 4-inch steel balls hammer the ore. After 6 hours of spinning, the rock becomes dust. This dust gets mixed with water. You get a liquid slurry. It runs through magnetic separators. Nickel ore is weakly magnetic, but the iron in it magnetizes stronger. Some of the waste rock gets filtered out. Nickel concentration in the slurry jumps from 2 to 4%. Still not much, but better. The slurry thickens in huge settling tanks. Water drains away, leaving wet paste. It dries in drum dryers at 400 degrees. What comes out is dry concentrate, ready for smelting. From 1,000 tons of ore, you get 300 tons of concentrate. (1751). Swedish chemist Axel Kronstedt is studying a strange mineral from the Los Mine. The rock's reddish, looks like copper ore. Kronstedt tries to smelt copper from it, but gets a white metal unlike anything known. Hard, heavy, doesn't rust. He names it nickel, after Nickel the mountain spirit from German folklore who tricked miners by slipping them worthless rocks instead of copper. But nickel turned out to be anything but worthless. In the 19th century, they start adding it to steel. The British discover that 5% nickel makes battleship armor twice as strong. The Germans use nickel steel for artillery. World War I turns nickel into a strategic resource. Whoever controls nickel controls military production. In the 30s, metallurgist Harry Brearley invents stainless steel. The formula is simple: 18% chromium, 8% nickel, the rest iron. This steel never rusts. Revolution in kitchens, hospitals, factories. Demand for nickel explodes. The hunt for new deposits begins worldwide. The 1960s. Discovery of massive deposits in New Caledonia and Indonesia. Laterite ores containing billions of tons of nickel. But there's a problem. These ores can't be smelted the conventional way. Too many impurities, compositions too complex. New technology is needed. The Canadians invent the Sherritt-Gordon process. The Chinese develop a pyrometallurgical method called RKEF. Rotary kiln, electric furnace, ferrochrome. Every country creates its own nickel extraction methods. By the 2000s, China becomes the dominant processor. They build dozens of plants in Indonesia and the Philippines. Strategy's simple. Control the processing, control the market. The US took a different path. Americans focus on high-purity nickel for EV batteries and reactors. Smaller volumes, but the highest quality. A plant in Ontario processes Canadian ore using flash smelting technology. Temperatures above 2,900 degrees Fahrenheit. Metal purity, 99.999%. This nickel goes into Teslas and nuclear submarines. Two approaches, two philosophies. China wins through volume, America through quality. The smelting shop is the hottest place in the plant. In the center of the hall stands an electric furnace as tall as a 5-story building. Power output, 100 megawatts. That's like 10,000 homes running simultaneously. Nickel ore concentrate is loaded from the top along with coke and fluxes. Coke is pure carbon, the heat source. Fluxes, limestone and quartz, they bind the waste rock. Through graphite electrodes, they run a current of 100,000 amps. Voltage, 200 volts. Temperature inside the furnace climbs to 1,500 degrees in an hour. The ore melts. Heavy metals, nickel, iron, cobalt, settle to the bottom. Light slag floats to the top. This separation is critical. After 8 hours of smelting, the furnace is ready for tapping. A tap hole opens at the bottom. Molten metal flows through a channel into a ladle. It glows white-hot. Temperature 1,400 degrees. Workers in silver suits control the process remotely. One ladle holds 50 tons of metal. This is matte, an alloy of nickel, iron, and sulfur. Nickel content, 20%. That's not enough. Further refining is needed. They pour the matte into a converter, a massive horizontal barrel 50 feet long. Oxygen gets added too. The blow begins. Oxygen at 150 psi blasts into the molten mix through tuyères. The reaction's exothermic. Releases so much heat the temperature shoots up to 3,000 degrees without any external heating. Sulfur and iron oxidize, burn off. New slag forms, gets drained away. After 6 hours of blowing, what's left in the converter is fine matte, an alloy with 50% nickel. But even that's not pure enough for high-tech applications. Next stage, electrolysis. The fine matte gets ground into powder and dissolved in sulfuric acid at 180 degrees. You get a green solution of nickel sulfate. This solution goes into electrolytic cells. Each cell, a tank 10 feet by 7, 3 feet deep. Inside hang titanium anodes and nickel cathodes. Between them, the solution. They run a current at 2 volts, current strength, 20,000 amps per cell. Nickel from the solution plates onto the cathodes. Over a week, each cathode builds up a layer of pure nickel about an inch thick. They pull the cathodes out, scrape off the nickel. Purity, 99.95%. And just like that, after passing through explosions, crushing, smelting at temperatures above 2,700 degrees Fahrenheit, oxidation, dissolving in acids and electrolysis, a dull gray rock transforms into a shining metal that changed the world. Without nickel, there'd be no skyscrapers, their steel frames would rust away in years. No submarines. Seawater would eat through their hulls. No nuclear reactors. Their pipes couldn't handle the corrosive environment. Every component that needs to last decades in conditions where ordinary steel surrenders contains nickel. 3 million tons per year. 200 consumer nations. Thousands of factories, millions of jobs. Indonesia digs the ore, China smelts the metal, America turns it into superalloys for space. Europe stamps out stainless steel for hospitals. A closed loop that keeps civilization afloat. Nickel isn't just a metal. It's a guarantee of durability for everything we build. Proof that humans learn to take nature's dull rocks and turn them into eternity. Every time you wash your hands in a sink that gleams like new after 20 years of service, remember, that's nickel at work. The metal that conquered time and corrosion.
Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break. doesn't bend, doesn't crack. For decades. How does a 4mm sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes.
It all starts in the raw materials warehouse, and the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport: chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part: forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method: shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a 3-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside: stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted.
And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work, riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting. When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick. And every fraction of that journey, someone's work, someone's inspection, someone's craft. Hey folks, on this channel, we go where cameras usually aren't allowed. If you dig these behind-the-scenes deep dives, hit subscribe and smash that bell so you don't miss new episodes. Today, I'm showing you how they make those manhole covers we walk over every day without even thinking about it. Turns out, it's way more interesting than you'd expect. I'm standing in the middle of a foundry floor, and it's about 110 degrees Fahrenheit in here. Sweat's pouring down like crazy, my glasses are fogged up, and the air's thick with the smell of molten metal and coal. Black coke dust crunches under my feet, and in the distance, a furnace pulses with a crimson glow. Come with me. I'll show you everything from the first ladle of molten metal to the finished cover. I'm met by the foundry master, a man in his 60s, with hands scarred by thousands of sparks. He's worked here for 38 years and says he's seen manhole covers cast for every major city. His creations lie everywhere beneath our feet. It all starts with scrap metal, massive piles of old cast iron, engine fragments, pipes, radiators, even old manhole covers that have served their time. Cast iron can be remelted an infinite number of times without losing its properties. It's one of the few things humanity gets right. Metal recycling here is 100%. The scrap is sorted by composition, weighed, and crane-loaded into a cupola furnace, a massive furnace about 30 feet tall, resembling a medieval tower. Inside, layers of coke and cast iron scrap alternate. The coke burns at around 2,700 degrees Fahrenheit, and at that temperature, the cast iron melts, transforming into a glowing orange liquid that flows to the bottom of the furnace. I stepped closer, as close as safety regulations would allow, and felt the skin on my face instantly tighten from the heat. At 15 feet, the temperature is so intense you want to back away. But the workers stand right by the furnace in special reflective suits, looking like astronauts. When the iron's melted, they release it into a ladle, a massive metal scoop that holds about 2,000 pounds. The ladle hangs from a crane and glides smoothly over rows of sand molds laid out across the factory floor. Each mold is the negative of a future manhole cover, an imprint of every detail, every letter, every ridge. The molds are made from special sand mixed with clay and water. A master craftsman showed me how it works. They take a wooden or metal model of the cover, press it into the sand, then carefully lift it out. What's left is a perfect impression. Every line, every curve, copied with accuracy down to a few thousandths of an inch. They place the second half of the mold on top, and you've got a cavity ready for the metal. A single model can produce thousands of impressions before it needs replacing. The coolest part? The text on the manhole covers. Each one shows the name of the city or water department. The letters are made separately. Small wooden or plastic type pieces get pressed into the sand in just the right spots. When the iron hardens, the text pops out. That's why all the words on manhole covers are mirror images of what was in the mold. Now comes the most spectacular part, the pour. Two workers in silver suits tilt the ladle, and out flows a stream of molten iron. It glows so bright you can't look at it without protective glasses. Your eyes start watering after a couple seconds. The metal hits 2,600 degrees Fahrenheit. The iron fills the mold in 5 seconds flat. But you've got to pour carefully. Too fast and the metal traps air, creating pockets inside the manhole. That cover will be weak and could crack under the weight of a truck. Too slow, and the metal starts hardening on the way down, filling the mold unevenly. An experienced foundry worker feels the right speed instinctively. It's a skill that takes years to develop. The sand mold starts smoking after the pour, moisture from the sand and clay evaporating. The smoke is thick, gray, smells like scorched earth. Ventilation runs full blast, but visibility in the shop still drops to about 50 feet. Then comes the waiting. The iron needs to cool, but not too fast. Slow cooling is what gives the metal its proper structure and strength. Open the mold too early, and the manhole cover warps from the sudden temperature shift. Scrap. The sweet spot is 18 hours. During that time, temperature gradually drops from about 2,550 degrees Fahrenheit down to around 210. The molds sit in rows on the shop floor, radiating steady, dry heat, like a radiator. Next day, workers smash the sand molds with hammers, and out come the manholes, still hot, dark gray, coated in sand residue. They look rough, messy, nothing like those smooth covers lying in the streets. Each manhole cover weighs between 66 and 132 pounds, depending on the size. A standard cover for city sewers runs about 24 inches in diameter and weighs roughly 95 pounds. I tried lifting one, barely got it off the ground. The foreman laughed. He's been lifting 10 of these a day for nearly 40 years. Next, the covers go to processing. A special machine with rotating steel cable brushes cleans off any remaining sand. Sparks fly in every direction. The metal gradually takes on a clean gray color. Pneumatic hammers knock off the flash, leftover metal that solidified in the wrong places. The most critical step is machining the seating surface. The cover's edge has to fit the frame perfectly or it'll rattle under traffic. Tolerance, about 1/10 of an inch. A lathe turns the edge to perfect roundness, and every cover has small holes, 2 or 4. They're for the special hook utility workers use to pull covers out. Without them, lifting a 95-pound cast iron lid off a flat surface is basically impossible. The quality control here is amazing. An inspector just taps each manhole cover with a small hammer and listens to the sound. If the sound is clean and ringing, the cover's good. If it's dull or has an off tone, there's a crack or void inside somewhere, and that cover gets scrapped. He checks 200 covers a day and says he's never wrong. I ask why manhole covers are round. Seems like square ones would be simpler to make. The foreman explained something brilliantly simple. A round cover can never fall through its own hole. A square one can be turned diagonally and drop right down. A circle is always bigger than its opening, no matter how you turn it. That's why manhole covers are round all over the world. It's not tradition, it's math. Another detail, the pattern on the surface. Those grooved lines, stars, or grid patterns aren't there for looks. It's an anti-slip coating. Smooth cast iron in the rain is slippery as ice. With the ridges, traction is way better. I stood on one cover right there in the shop, held firm even in work boots with smooth soles. Finished manhole covers get stacked 10 to a pile and shipped out to cities. Each stack weighs around 900 to 1,100 pounds, so they only load them with a crane. One factory produces 50,000 covers a year. Sounds like a lot, but a major city alone might have over 300,000 manholes. That means every few years, every single cover needs replacing. Why so often? The covers break down. Sand and salt in winter, vibrations from trucks, temperature swings from -22 to 130 Fahrenheit on the asphalt in summer. Cast iron is tough, but it's not forever. average lifespan is 30 years, and in high-traffic areas, just 5. There are covers for steam tunnels, telephone, electrical, water mains. Each type differs slightly in size and thickness. The thickest ones are for highways, where they get run over by trucks weighing 36 tons. There, the wall thickness hits 2 inches. The Factory Museum holds old manhole covers, the oldest one from 1892. Over 130 years old, and it's still intact. The cast iron's dark, smooth from time, but not a single crack. There are covers from different countries: France, Japan, England. The Japanese ones are the most beautiful, engraved with cherry blossoms or mountains. Over there, manhole covers are art. When I left the factory, there was an ordinary manhole cover lying in the street. I stopped, crouched down, ran my hand across its surface. Now, I see it differently. This isn't just a lid. This is 2,700 degrees of heat, 18 hours of waiting, precision down to 1/10 of an inch, workers' hands in silver suits, and the ring of an inspector's hammer. Every manhole cover beneath our feet has been through this journey and will last another 30 years, bearing thousands of tons, millions of footsteps, rain, snow, and heat.
Every year, dozens of nuclear submarines get retired around the world. Steel giants weighing over 10,000 tons. Inside each one sits a reactor pumping out hundreds of megawatts. But what happens when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that lasts for months? Temperatures here hit 14,000 degrees Fahrenheit. A mistake isn't measured in seconds, it's measured in centuries. In this video, you'll see the decommissioning process from the first cut to the last ton of melted metal, and find out what becomes of a submarine giant's armor. The process begins with the most dangerous stage, removing the spent nuclear fuel. The submarine is moved into a special enclosed dock. Around it, a real scientific laboratory unfolds. This is a battle against invisible radiation. It doesn't last days, it lasts months. Inside the reactor core are fuel assemblies. They've kept this monster alive for decades. Each assembly is a bundle of thin zirconium tubes, about half an inch in diameter. Inside, uranium dioxide pellets. One assembly is 13 feet long. Weight, 660 pounds. The reactor holds 100 to 120 of them. They're removed using remote manipulators. Each assembly emits a lethal dose of radiation, 500 roentgens per hour at 3 feet. That'll kill a person in an hour. The assembly is lifted by a crane rated for 20 tons and lowered into a lead container. Container wall thickness, 10 inches of pure lead. Container weight, 17,000 pounds. Only lead stops gamma radiation. The containers are loaded into special rail cars with water cooling and shipped to temporary storage. This stage takes 3 to 4 months of continuous work. If you're interested in seeing how things built for war get taken apart, subscribe to the channel. Here we show you production processes hidden from view. Once the fuel's extracted, it's time for the reactor compartment. This is a massive section of the sub. Weight, 1,500 tons. Length, 33 feet. Diameter, 30 feet. Engineers don't dismantle the reactor piece by piece. Too dangerous. The metal itself is radioactive. Neutron flux from the operating reactor bombarded the steel for years. Iron atoms transformed into radioactive isotopes, so they cut out the entire compartment whole. They use oxyacetylene torches. Flame temperature, 5,800 degrees Fahrenheit. Mix of acetylene and oxygen. Feed pressure, 217 pounds per square inch. The torch burns through 3-inch thick steel in 10 minutes. They cut in a ring around the compartment. 2 cuts, forward and aft. You get a cylinder. All technological openings are welded shut with half-inch steel plates. Welding, electric arc, 1/4-inch diameter electrodes. Current, 350 amps. You get a sealed capsule. It's lifted by a 200-ton crane and loaded onto a barge. The barge is towed to a burial site. In Russia, that's Novaya Zemlya. In the US, Hanford site. There, the capsules are placed in concrete trenches 65 feet deep, covered with earth on top. They'll sit there 300 years until radiation levels drop to background. Decontamination is the longest phase. The reactor compartment's cut out and shipped off, but the work's just beginning. Decades of coolant circulation left their mark. Thousands of feet of primary loop piping, pumps, heat exchangers, steam generators, all of it contaminated. Radioactive isotopes soaked into the metal. That's induced radiation. Teams in protective suits scan every foot, hunting for hotspots, areas with elevated readings. They use DP5B dosimeters. Sensitivity, 0.01 milliroentgen per hour. Every pipe gets checked, every pump, every valve. Then chemical flushing begins. They run acid solutions through the primary loop piping. Sulfuric acid at 10% concentration. Temperature 140 degrees Fahrenheit. Pressure 115 psi. The acid dissolves the oxide film off pipe walls. Radioactive isotopes go with it. Solution gets collected in 13,000-gallon tanks, filtered through ion exchange resins. radionuclides precipitate onto the resin. Resin gets incinerated at 2200 degrees Fahrenheit. You get ash. Mix the ash with cement and pour it into concrete containers. That's Class 2 radioactive waste. Chemistry doesn't work everywhere. Valves, gate valves, filters, they dismantle those by hand. Teams of 3. Shifts last 30 minutes. Can't go longer, the dose accumulates. Every part gets packed in a lead box. Box weighs 265 pounds. Walls, 4 inches of lead. If contamination levels run too high, they encase the part in concrete right inside the hull. Special attention goes to the reactor's biological shield. Massive plates of lead and polyethylene. Lead layer, 6 inches thick. Polyethylene, 12 inches. Lead stops gamma rays. Polyethylene slows neutrons. Weight per plate, 4 tons. 8 plates total. They pull each one with a crane. Decontaminate with ultrasound. Frequency, 40 kilohertz. Power, 3 kilowatts. Ultrasound breaks down the oxide film. Then they rinse the plate with alkaline solution and dry it with hot air at 250 degrees. Only after thousands of air samples and surface swabs, when everything reads 0, they open the dock to regular workers. Now it's not a nuclear facility, it's just a complex steel structure. Cutting the hull. After decontamination, the submarine is ready for final dismantling. The submarine's hull isn't ordinary metal, it's an alloy built for war. It withstands water pressure at depths of 1,000 to 1,300 feet. That's 30 to 40 atmospheres. Hull thickness, 3 to 4 inches. A K29 grade steel. Tensile strength, 100,000 pounds per square inch. Regular cutters won't touch it. They use plasma torches. Plasma is ionized gas. An electric arc creates the temperature. Voltage, 300 volts. Current, 400 amps. Power, 120 kilowatts. Argon gets blown through a nozzle 1/8 inch across. Pressure, 90 pounds per square inch. Flow rate, 1 cubic foot per minute. The arc heats the argon to 15,000 degrees Fahrenheit. That's 1.5 times hotter than the surface of the sun. The plasma jet shoots from the nozzle at 670 miles per hour. That's the speed of sound. Under that stream, 4-inch thick steel melts in 5 seconds. The torch follows the marked line. Cutting speed, 8 inches per minute. Sparks and smoke fly from the torch. Flame height, 10 feet. Spark temperature, 1,800 degrees. The second tool, oxygen lances, a 10-foot steel pipe, 1-inch diameter. Inside, a bundle of steel rods, each about 1/6 of an inch thick. Pure oxygen flows through the pipe at 150 psi. Flow rate, 50 cubic feet per minute. The rods are ignited with an acetylene torch. They start burning in the oxygen. Steel burns. Massive amounts of heat pour out. Temperature in the burn zone, 6,900 degrees Fahrenheit. The lance burns clean through the steel, leaves a molten seam 2 inches wide, burn through speed, 20 inches per minute, faster than plasma. But it takes serious skill. You guide the lance dead perpendicular. Deviate more than 10 degrees and the burn's incomplete. Crews of 4. Protective suits made of Kevlar. Masks with number 13 filters. They block infrared and ultraviolet radiation. Without the mask, your retina burns in 1 second. They cut from bow and stern, working gradually toward the center. The hull gets cut into cylindrical sections, each section 20 feet long, 30 feet in diameter. Weight, 400 tons. Cranes rated for 800 tons lift the sections and stack them in the sorting zone. Metal sorting. Every hull fragment gets checked again with dosimeters. They're hunting for isotope traces in microcracks and weld seams. If the device clicks, the fragment gets isolated, sent for recleaning or special disposal. Only clean metal receives a safety certificate. It can leave the shipyard territory, then sorting by chemical composition. Steel grades HY80 and HY100. These are high-strength steels. Nickel content, 8%. Chromium, 2%. Molybdenum, 1%. These alloying elements are treasure for metallurgists. Nickel provides toughness. Chromium, corrosion resistance. Molybdenum, strength at high temperatures. Regular hull steel. AK-29 gets sent for remelting separately. Titanium parts, the sail, fairings, also separate. Titanium doesn't melt with steel. Different melting points. Titanium, 3,034 degrees Fahrenheit. Steel, 2,795. Copper alloys, wiring, heat exchangers, to non-ferrous metal. Aluminum alloys, bulkheads, ladders, to aluminum scrap. Reborn in fire. High-strength steel heads to the metallurgical plant. Loaded into an electric arc furnace. Capacity, 100 tons. 3 graphite electrodes, 24 inches in diameter. 600 volts, 60,000 amps. 36 megawatts of raw power. An arc ignites between the electrodes and metal. The arc zone hits 6,300 degrees Fahrenheit. Metal melts, becomes a liquid lake. The melt reaches 3,000 degrees. Melting time, 3 hours. Lab techs pull samples every 30 minutes. Analyze composition on a spectrometer. Adjust with ferroalloy additives. Precision matters. Carbon tolerance, plus or minus 0.05%. Nickel, plus or minus 0.1%. Finished melt pours into a ladle. The ladle weighs 200 tons. From the ladle, it flows into molds. Create slabs, steel plates. 6.5 feet by 20 feet. 10 inches thick. 23 tons each. Slabs get rolled into sheets or cut into rebar stock. Yesterday's warship armor plating becomes a river bridge support or a skyscraper skeleton. Steel that once withstood depth charges now holds up bridges. Metal doesn't die. It lives again. If you found this fascinating, hit that like button. Drop a comment. Did you know submarines get recycled for 300 years? Subscribe. We show you how the old dies and the new is born.
A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane. 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit 2 Airbus A350 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings, and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and Dehard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous Beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet, like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, piston diameter 4.7 inches, pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber, layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first Beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust? 320 kilonewtons, 72,000 pounds of force. Fan diameter, 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque, 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June, ground testing. 200,000 checkpoint inspections. Every sensor checked, every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018. Blagnac, Toulouse. First flight, crew of 6, 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2700 degrees. Fuel burn 12 tons per hour. 120 knots, 222 kilometers per hour. Nose wheel liftoff. 140 knots, main gear liftoff. Climb rate 1,000 feet per minute. Flight level 350, 35,000 feet. Cruise speed 0.69 Mach, 466 miles per hour. 4 hours, 20 minutes airborne. Landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. Minus 22 in Sweden, plus 113 in Spain. Everything works. November 13th, 2019. Type certificate. The Beluga cleared for flight.
January 9th, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo, 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain, fuselages in Germany, final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed. Imagine a material born from sand and stone, fired at temperatures exceeding 2,000 degrees Fahrenheit, stretched into threads thinner than a human hair, then transformed into either building insulation, boat components, pipes, composite beams, turbine blades, or even heavy-duty industrial structures. This is fiberglass, one of the most underestimated materials in modern industry. At first glance, it seems ordinary. Insulation here, composites there, holes and panels everywhere. But beneath this ordinariness lies an incredibly powerful technology. Because fiberglass isn't just melted glass pulled into threads. It's a meticulously calibrated industrial process where chemical composition, melting temperature, drawing speed, protective coating properties, and subsequent processing methods determine whether the material becomes brittle garbage or the foundation for strong, lightweight engineered products. And today, we're breaking down how fiberglass is manufactured for industry, why it's simultaneously light and strong, what forms it takes, and how one of the most versatile materials in modern engineering is born from molten glass. Everything starts with raw materials, and here's one of fiberglass's biggest paradoxes. The base is incredibly simple: silica sand, limestone, soda ash, and a few mineral additives. But it's the combination of these ingredients that determines the fiber's future properties. Pure quartz alone needs extremely high melting temperatures, so manufacturers add substances to control the process and change the final product's characteristics. Additives can boost chemical resistance, improve electrical properties, increase strength, or tailor the material for composites and insulation. Industry uses different types of glass. Some work best for general applications, others for chemically aggressive environments, still others for higher mechanical strength. So fiberglass production doesn't just start with dumping sand into a furnace. It starts with precise formulation. At this stage, the material still looks like ordinary mineral mix, but this is where its future role gets locked in. Whether it'll be cheap insulation, reinforcing fabric, or the foundation for complex composite structures.
The next stage is melting. The prepared mixture gets sent into massive furnaces, where at temperatures around 2,500 to 2,550 degrees Fahrenheit, sometimes even higher, the raw materials transform into a uniform glass mass. Pure quartz requires even higher temps. But the key part of this stage isn't just the heating itself, it's controlling the state of the melt. The furnace is divided into zones so the material doesn't just melt, it purges bubbles, becomes uniform in composition, and hits the exact viscosity needed. If the melt is unstable, if impurities or air pockets remain, the future fibers will have weak spots. And in a material that needs to be both thin and strong, even microscopic defects are critical. Essentially, at this stage, the plant isn't just creating liquid glass. It's creating a high-precision industrial melt that has to behave perfectly in the next phase. Because what comes next isn't pouring it into a mold, it's turning it into threads. And for that, the glass needs nearly jeweler-grade precision in temperature and flow. The most impressive stage? Turning molten glass into filaments. Liquid glass flows to special spinnerets. The industry calls them bushings. These are plates made from an expensive, incredibly resilient alloy of platinum and rhodium. The glass passes through hundreds, sometimes thousands, of microscopic holes. From each hole emerges a hair-thin stream of white-hot material. But that stream isn't fiber yet. Real fiber is born in the drawing process. High-speed mechanisms literally yank the glass downward at tremendous velocity, and that force transforms the molten mass into ultra-fine continuous filaments. We're talking diameters measured in micrometers, several times thinner than a human hair. It's the drawing speed and rapid cooling that prevent the glass from crystallizing like ordinary, brittle material. Instead, you get an amorphous glass filament with engineered properties. And here's where you really see it. Fiberglass isn't just molten glass, it's a material born at the intersection of fire, velocity, and precision mechanics. But just pulling the fiber isn't enough. Glass by itself is brittle, and if you leave fresh filaments unprotected, they'll start getting damaged, rubbing against each other, and quickly losing their properties. So almost immediately after drawing, the fibers get a special chemical coating, sizing. This is one of the most underrated yet crucial elements of the entire technology. This coating doesn't just reduce friction and protect the fibers from breaking during winding, it also preps them for their future work in composites, improving the bond between smooth glass and the resin that'll later hold the fibers together in the finished product. The right sizing determines how well the fiberglass will interact with polyester, epoxy, or other matrices. In other words, this is where it's decided whether the glass strand becomes just a bundle of brittle fibers or a full-fledged reinforcing material capable of performing in real-world structures. Sometimes it seems like fiberglass strength is all about the glass itself, but in reality, much of it comes down to the chemistry of its surface. Next comes the transformation of fibers into semi-finished products. Threads are gathered into strands, rovings, wound onto spools, chopped into short fragments, formed into mats, fabrics, or specialized directional reinforcement structures. And this is where fiberglass splits into two major application worlds. The first is insulation. Here, the fibers are made more random, turned into a bulky mat, bound with special compounds, and you get a material that traps air incredibly well, which means it traps heat and sound. The second world is composites. Here, the glass fibers don't just sit in a loose layer. They become a reinforcing framework for resins. These combinations produce boat hulls, panels, pipes, profiles, tanks, industrial flooring, and countless other products. Some applications use woven roving, others use chop strand mat. Still others use directional knitted structures where fibers are oriented for specific loads. In other words, fiberglass isn't one product. It's a family of industrial forms that starts with the same thread, but ends with wildly different application technologies. The story of fiberglass and industrial profiles is especially fascinating. When glass fiber meets resin, it stops being just a bundle of threads. It transforms into a composite where each material handles its own job. Resin handles compression beautifully, locks in shape, and spreads the load. Glass fibers excel at tension. It's roughly the same logic as reinforced concrete, where concrete and steel rebar compensate for each other's weaknesses. This combination makes fiberglass light, strong, corrosion-resistant, and easy to mold into all kinds of shapes. One of the most important industrial methods is pultrusion. Fibers get pulled through resin and a heated die, producing continuous profiles with constant cross-sections. That's how you make beams, angles, tubes, sheets, grating, and other elements that work where metal is too heavy, rusts, or fails on electrical and thermal properties. That's where the power of fiberglass hides. It lets you create structural materials from what seems like an incredibly fragile starting point. So why is fiberglass both lightweight and strong? The secret's in the scale and structure. The thinner the glass fiber and the fewer defects on its surface, the higher its mechanical strength. And when lots of these fibers combine into a smart shape and work together with resin, you get a material with an incredibly high strength-to-weight ratio. That's exactly why fiberglass and fiberglass-based composites are so widely used in transportation, construction, energy, and manufacturing. It doesn't replace metal absolutely everywhere, but it works beautifully where you need a combination of low weight, corrosion resistance, electrical insulation, and solid mechanical durability. Plus, fiberglass can be adapted for different tasks by changing the glass composition, fiber type, reinforcement direction, and matrix properties. That's how you end up with a material that can be a soft insulation blanket, a rigid composite beam, or part of a complex industrial system. And all of it from sand, minerals, heat, and incredibly precise technology.
"60 days. That's exactly how long it takes for an empty Coke can to become a brand new can on a store shelf. You finish your drink, toss the can in the trash, and 2 months later that same can is back in the supermarket. But this isn't magic. It's aluminum recycling, the most profitable recycling process on the planet. Every recycled can saves 95% of the energy compared to making new aluminum. It's like the difference between taking a walk and flying to another continent. Every year, 600 billion aluminum cans get recycled worldwide. Weight, 20 million tons. Value, $50 billion. And here's the most amazing part. Aluminum can be recycled infinitely, without losing quality. Metal that's been melted down 1,000 times is identical to fresh aluminum. How is that possible? How does a dirty crushed can turn into a perfectly clean sheet of metal? Stick around till the end. You'll see the most perfect closed-loop system ever created by humans. Every second, 20,000 aluminum cans get tossed worldwide. In a minute, over 1 million. In a day, 1.5 billion. That's a mountain of metal as tall as Everest, and all of it needs collecting, sorting, recycling. The process starts on city streets. Blue-marked trash bins went for recyclables. Trucks gather the contents and haul them to sorting facilities. Conveyor belts here stretch over 300 feet. Everything moves down the line. Cans, bottles, cardboard, plastic. The job? Separate aluminum from everything else. And this is where technology kicks in. Powerful electromagnets hang above the conveyor. But aluminum isn't magnetic. So how do you pull it out? The magnets create eddy currents. A rapidly changing magnetic field induces a current in the aluminum, and that current creates its own field. This field repels the cans away from the conveyor. They literally jump up and fly into a separate bin. One separator processes 15 tons of trash per hour. Pure aluminum drops into the collector. Everything else keeps moving down the line. Next up, cleaning and prep. Cans arrive dirty. Beverage residue, labels, paint. All of it's gotta go. Cans get loaded into massive drums. 10 feet across, 30 feet long. Inside, water and alkaline solution. The drum spins. Cans scrub against each other. Dirt, labels, paint wash away. Water drains through filters, leaves nothing but clean metal. Then drying. Hot air at 300 degrees. Fahrenheit evaporates moisture in 15 minutes. Now the cans need compressing. A hydraulic press generates 300 tons of pressure. 1,000 cans become a dense block weighing 45 pounds. These blocks are called bales, easy to store and transport. A truck can haul 15 tons of bales. That's 750,000 cans. Bales get stacked in open yards. Aluminum doesn't rust, rain can't hurt it. It waits its turn for remelting. Some blocks sit a week, others a month. But they all end up in the same place eventually, the melting furnace. (1827). German chemist Friedrich Wöhler produces pure aluminum for the first time. Tiny beads of silvery metal. Light as wood, but strong as iron. Beautiful as silver, but it doesn't tarnish. The world goes crazy. Aluminum gets called the metal of kings. Its price, $1,200 per kilogram. That's 3 times more expensive than gold. French Emperor Napoleon III orders aluminum silverware for his most important guests. Everyone else eats with gold, it's cheaper. The problem is, aluminum is incredibly hard to extract. It's hidden in ore, bauxite. Extracting it chemically is nearly impossible. You need tons of reagents and weeks of work for a single gram of metal. Things change in 1886. American Charles Hall and Frenchman Paul Héroult independently invent the electrolytic process. You run current through molten ore. You get pure aluminum. Simple, fast, cheap. The price drops from $1,000 to $2 in 20 years. The aluminum revolution begins. The 20th century turned aluminum into the planet's most widely used non-ferrous metal. Airplanes, cars, electrical wiring, beverage cans, aluminum everywhere. By the 70s, global production hits 10 million tons a year. But there's a problem. Producing aluminum from ore demands monstrous amounts of energy. To get 1 ton of metal, you need 15,000 kilowatt hours of electricity. That's a year's worth of power for the average American home. Plus carbon dioxide emissions, landscape destruction from open pit mines. Environmentalists sound the alarm. Then someone grasps the obvious. Aluminum doesn't degrade. A can tossed in the forest will sit there 200 years unchanged. But what if you melt it down? Energy cost? Just 700 kilowatt hours per ton. 20 times the savings. No need to mine ore, no need for chemical reagents, no need for giant electrolyzers. Just melt the metal and use it again. The recycling era begins. In the US during the 70s, 15% of cans got recycled. Now, 50%. In Brazil, 98%. That's the highest recycling rate of any material. The smelting shop. Air temperature near the ceiling, 122 degrees Fahrenheit. In the center of the hall stands a furnace as tall as a 3-story building. They call it a reverberatory furnace. Inside, a bath of molten aluminum. Temperature, 1400 degrees Fahrenheit. The metal glows orange. Heat dances above it. Briquettes feed in by conveyor straight into the furnace. The aluminum melts instantly, melting point, just 1220 degrees. That's 2.5 times less than steel. The energy savings are massive, but trash floats in the melt. Paint residue, varnish, impurities from other metals. They need to be removed. Chlorine gets blown into the bath. The gas rises in bubbles through the melt. It binds the impurities and carries them to the surface. Dross forms, gray foam. It's scraped off with mechanical rakes. Beneath the dross, a mirror of pure metal. After 6 hours of melting, the furnace is ready to tap. A massive ladle rolls in from below. The furnace tilts and the melt pours out in a golden stream. One ladle holds 20 tons. That's 1 million cans in liquid form. The molten metal gets poured from the ladle into molds. Out come ingots weighing 25 tons each. Length, 33 feet. Width, 5 feet. Thickness, 20 inches. They cool for 24 hours. Temperature drops from 1300 degrees Fahrenheit to room temperature. The ingot solidifies but stays soft and pliable. That's aluminum for you. It deforms easily. Next stage, rolling. The ingot heads to the rolling mill. This giant machine has rollers 6.5 feet across. The ingot passes between the rollers. Pressure, 1,000 tons. The metal flattens like dough. In one pass, thickness shrinks from 20 inches to 8. The ingot passes through the rollers again. Now it's 4 inches thick. Another pass, 2 inches. Another, under 1 inch. The process repeats 20 times. At the end, you get a sheet about 1/10 of an inch thick. It comes out of the mill over half a mile long, rolled into a coil weighing 10 tons. One coil makes 30,000 cans. The metal ships to the packaging plant. There they stamp blanks from the sheet, stretch the walls, form the neck. Circle complete. 60 days after hitting the trash, the can's back on the shelf. And that's how aluminum lives forever. The metal atoms in your Coke can right now might have been part of a World War II aircraft. Then became a house roof in the 50s. Then power line cables in the 80s. Then a bicycle frame in the 2000s. And now, a can in your hand. Tomorrow, they'll become part of a laptop. The day after, the skin of a spacecraft. Aluminum doesn't know aging. Each remelt returns its youth. It's the only material on the planet that can be used infinitely without degrading. Humanity produces 100 million tons of aluminum a year. 75% of all the metal ever produced is still in use today. Imagine, metal cast 100 years ago is working right now. Aluminum recycling isn't just waste processing, it's a philosophy of matter's immortality. Proof that in the right hands, the planet's resources are inexhaustible. Every can you toss isn't trash. It's a stockpile of metal for future generations. A closed loop, eternal rebirth. Aluminum will outlive civilizations and will serve those who come after us.
Each year, the world burns energy equivalent to the power of thousands of volcanoes. And all of this is contained thanks to a material almost no one thinks about: refractory brick. Its market exceeds 30 billion euros, and more than 70% of this mass is consumed by a single industry: metallurgy. Just to line one blast furnace requires up to 4,000 tons of such brick. How does ordinary clay transform into stone capable of withstanding over 1,600 degrees? And why, without this material, would factories, plants, and even our fireplaces grind to a halt? Watch carefully. Everything will become clear. At the heart of it all lies not ordinary red clay, but a particular variety, refractory clay, or kaolin. Its uniqueness derives from its chemical composition, dominated by two oxides, aluminum oxide and silicon dioxide. It is precisely their elevated content that endows the raw material with its principal characteristic, an extraordinarily high melting point. To impart stability to the finished product, manufacturers employ a rather cunning technical stratagem. A portion of the extracted clay is not sent directly into production, but is first fired in kilns at temperatures reaching up to 1500 degrees. Through this process, the clay loses its plasticity and transforms into an exceedingly hard, stone-like material known as shamat.
This prepared shamat is then crushed and used as the principal component, with a specified quantity of fresh plastic clay added to it, which acts as a binder. This approach solves a key problem. It significantly reduces shrinkage of the products during final drying and firing, preventing warping and cracking. So, the process begins with the preparation of components. Extracted clay and pre-prepared shamat are fed to the grinding line. Giant crusher jaws split the large pieces, and then roller mills and ball mills relentlessly grind them down to a fine powder with a precisely defined grain size.
Following crushing, automated dosing systems weigh each component: grog powder, clay powder, water, with computerized precision according to the formula. This entire mixture is sent to powerful mixers, where it's intensively blended until an absolutely homogeneous mass, known as the batch, forms. Next, the shapeless mass must acquire its contours. The most common method is semi-dry pressing. The batch, containing minimal moisture, is loaded into high-strength metal molds. Then, a press bears down upon it with tremendous force, measured in hundreds of tons. Thanks to this colossal pressure, what emerges is a dense, smooth block with perfect geometry, a green brick. The next stage requires not strength, but patience and precision. The raw brick is carefully arranged on trolleys and dispatched to long tunnel dryers. This is a slow and delicate phase, which can last from 1 to several days. Inside the dryer, a meticulously controlled microclimate is maintained. Temperature gradually rises whilst humidity decreases. It is essential that moisture escapes from the brick as uniformly as possible. Any haste will result in the outer layers drying faster than the inner ones, which creates critical stresses and simply tears the brick apart with cracks from within. When all the water has been removed, the culmination arrives: firing. The brick enters the fiery tunnel of the kiln, where it awaits a true transformation. Moving slowly through different zones, it gradually heats to peak temperatures, which for fireclay brick reach 1,400 degrees, whilst for high alumina varieties may exceed 1,750 degrees. This is not merely drying, but a profound metamorphosis. At such temperatures, mineral particles soften and sinter together, forming a robust ceramic structure. Within the system of aluminum oxide and silicon dioxide, new crystalline compounds form, particularly needle-like mullite crystals, which, rather like reinforcement bars, permeate the entire structure of the brick, imparting exceptional strength to it. Having passed the peak heating stage, the brick moves just as slowly through the cooling zone. This phase is no less crucial, since rapid cooling would cause thermal shock and destroy the product. What emerges from the kiln is an entirely new entity, a hard, resonant, slightly rough-textured block that fears no fire. What follows is purely quality control. Each piece undergoes rigorous inspection for dimensional accuracy and absence of defects, after which it is marked, packaged, and dispatched to fulfill its principal purpose, to contain flame. To grasp the true significance of refractory brick, one need only consider the numbers. The global refractory materials market represents an industry valued at more than 30 billion euros annually, and over 70% of this colossal volume of product is consumed by a single sector: ferrous metallurgy.
The internal protective lining of one large blast furnace alone may require between 2,000 and 4,000 tons of refractories. And a single steel pouring ladle, which transports hundreds of tons of molten metal, gets through several complete sets of lining per year. The standard fire clay brick, grade Sha A, which is the most common type, weighs approximately 3.5 kilograms and is capable of withstanding temperatures up to 1,690 degrees Celsius. Refractory brick lines the interiors of blast furnaces, where pig iron is born from ore. It provides refractory lining for oxygen converters and electric arc furnaces, in which pig iron is transformed into steel. Enormous steel pouring ladles transporting molten metal are likewise protected internally by armor of refractories. Moreover, for each zone of the unit, a particular, specific type of brick is selected. The second most significant consumer is the cement industry. Long rotating kilns, several hundred meters in length, in which cement clinker is fired at temperatures of 1,450 degrees, are entirely lined internally with specialized varieties of refractory brick. The glass industry also cannot exist without refractories. Enormous tank furnaces, where glass mass is melted at temperatures of approximately 1,600 degrees, are lined with special, highly resistant types of brick, which are capable of withstanding for years not only the heat, but also the aggressive chemical action of molten glass. Besides these giants, refractory brick is used in thermal power engineering for lining boilers, in the chemical industry for lining reactors, and also in waste incineration furnaces. And, of course, on a far smaller scale, we encounter it in everyday life. It is precisely from Shamat brick that fireplaces, stoves, and chimneys are built, because it guarantees safety and longevity.
Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears, yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1,330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace, and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine, a 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between two rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees, so the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing? The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human? Couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat, 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out, shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity, 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible. Imagine if construction could be not just strong, but ultra lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually, and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal.
Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets.
It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. But installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics.
Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast's force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture. Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature, operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems, known as Christmas trees, that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world.
Imagine a part so perfect it can spin for 30 years without stopping. From tiny balls just 1/8 of an inch across to giants 30 feet tall holding up wind turbines. Bearings are a $120 billion a year industry. But their life begins in absolute chaos. Massive explosions, hellish fire, pressure that could crush a tank. How does raw metal become the heart of perfection? Today you'll follow the complete journey, from a quarry blast to the perfect ball spinning at 10,000 revolutions per minute. If you want to see how chaos turns into precision, subscribe to the channel. Here we show the manufacturing that builds our world. It all starts with a roar that shakes the ground for miles around. In the giant quarries of Australia and Brazil, iron ore hides in layers of rock hundreds of feet thick. Geologists turn the quarry into a chessboard. They drill boreholes 60 to 100 feet deep. Borehole diameter, 10 inches. Distance between boreholes, 16 feet. 1 square mile, 1,000 boreholes. Into each they pour explosives, a mix of ammonium nitrate and diesel fuel. Ratio 94 to 6%. Charge weight per borehole, 650 pounds. Detonation happens with millisecond delays. First borehole explodes. 20 milliseconds later, the second. 40 milliseconds, the third. The wave rolls across the entire field. In 10 seconds, they detonate 200 boreholes. They blast 3.5 million cubic feet of rock, energy equivalent to 110,000 pounds of TNT. But this isn't random chaos. This is planned destruction. Chunks of rock shoot 150 feet into the air. They fall. Dust rises over half a mile into the sky. When it settles, instead of a mountain, there lies 2 million tons of crushed ore. Giant excavators roll onto the site. The excavator bucket? 1,400 cubic feet. That's the volume of a small apartment. The bucket weighs 28 tons. One scoop? 100 tons of rock. They load it into dump trucks. Hauling capacity of each truck, 360 tons. Wheel height, 13 feet. Diameter, 11.5 feet. Weight of one wheel, 5 tons. Engine, 3,500 horsepower. Fuel consumption, 35 gallons per mile. The dump truck hauls ore to the crusher. Distance, 9 miles. Speed, 25 miles per hour. Travel time, 20 minutes. In one day, a single truck makes 30 trips, hauls 10,000 tons. 20 excavators and 60 dump trucks work the quarry. They move 300,000 tons of ore per day. That's 100 million tons a year. Crushing. Ore enters the jaw crusher. The crusher's mouth, 13 feet wide. The jaw weighs 120 tons. Jaw stroke, 12 inches. Oscillation frequency, 200 strikes per minute. Drive power, 1.5 megawatts. The crusher pulverizes yard-wide rocks into 8-inch chunks. Throughput, 2,000 tons per hour. From the jaw crusher, ore moves to the cone crusher. The cone spins inside the bowl at 150 revolutions per minute. Gap between cone and bowl, 1 inch. 8-inch pieces become 1-inch pieces. Then the ball mill. Cylinder 20 feet in diameter. Length 26 feet. Inside steel balls. Ball diameter 4 inches. Weight per ball 9 pounds. Total balls 50,000. Combined weight 200 tons. The mill rotates at 18 revolutions per minute. Balls drop from 6.5 feet. Impact grinds ore to powder. Particle size after milling 0.04 inches. The thickness of a human hair. Thickness. Flotation enrichment. Ore powder gets mixed with water, creates a slurry. Solid concentration, 30%. Add reagents. Potassium xanthate, 7 ounces per ton of ore. Pine oil, 1.8 ounces per ton. Xanthate makes iron particles hydrophobic. They repel water. Pour the slurry into the flotation machine. Tank volume, 13,000 gallons. Air pumps in from below. Pressure, 30 pounds per square inch. Flow rate, 10,000 cubic feet per hour. Air forms billions of bubbles 0.2 inches across. Bubbles stick to iron particles. Lift them up. Foam forms on the surface. Reddish gray. Dense. Iron content in the foam, 67%. Waste rock sinks to the bottom. Gets pumped out and dumped in tailings. Foam scraped off with blades, sent to filtration. Vacuum filter sucks out the water. Leaves a damp mass. Moisture content, 9%. That's concentrate. Gets turned into pellets. Pelletizing. The concentrate goes to a disc pelletizer. The disc is 15 feet across. Tilted at 45 degrees. Spins at 15 revolutions per minute. Powder feeds onto the disc. Water's added, 3% by weight. Centrifugal force rolls the powder into balls. Pellets come out 1/2 inch in diameter, give or take 1/16 of an inch. The pellets roll off the edge onto a conveyor. Output? 300 tons an hour. 1 million pellets every hour. The pellets head to the kiln. Firing temperature, 2450 degrees Fahrenheit. 20 minutes in the heat. The pellets turn rock hard. Crushing strength, 3,500 psi. Now they're ready for the blast furnace. Blast furnace smelting. Pellets are loaded into the blast furnace. The furnace stands 105 feet tall. The throat diameter, 40 feet. The hearth diameter, 26 feet. Furnace volume, 42,000 cubic feet. Loaded in layers. Pellet layer, 3 feet. Coke layer, 20 inches. Limestone layer, 8 inches. Hot air blasts in from below. Temperature, 2,200 degrees. Pressure, 60 pounds per square inch. Flow rate, 100,000 cubic feet per minute. The coke burns, carbon monoxide releases. It strips the iron from the pellets. Temperature in the hearth, 3,600 degrees. The iron melts, flows downward, pools in the hearth. Every 4 hours they tap the pig iron. They open the tap hole. Pig iron pours out like a river of fire. Temperature at 2,700 degrees. Color, bright orange. One tap, 300 tons. In 24 hours, the furnace produces 2,000 tons of pig iron. The pig iron contains 4% carbon. That's way too much. Pig iron's brittle. Needs converter smelting. Steel production. They pour pig iron into an oxygen converter. The converter holds 350 tons. A lance descends from above. The lance is 20 inches across. Pure oxygen blasts through the lance. Pressure hits 175 pounds per square inch. Flow rate, 18,000 cubic feet per minute. Jet velocity, 1,300 miles per hour. That's twice the speed of sound. Oxygen oxidizes the carbon burns. Turns into carbon dioxide. Flame shoots out the converter's mouth. Flame reaches 30 feet high. Temperature hits 3,600 degrees. The process takes 20 minutes. Carbon content drops from 4% down to 0.7%. This is bearing steel. Grade designation SAE 52100. Chromium content 1.5%. Chromium provides hardness and wear resistance. They pour the steel into a ladle, from the ladle into molds. Out come ingots, blanks weighing 5 tons each. Ingot dimensions 3 feet by 3 feet by 6 feet. Rolling and machining. Ingots are heated in a furnace to 2,200 degrees Fahrenheit. Rolled on a mill. Rollers 40 inches in diameter. Rolling force 2,000 tons. The ingot becomes rods 4 inches across. Rod length 20 feet. Rods are cut into blanks 8 inches long. Blanks are heated to 1,560 degrees. Stamped into rings on a press generating 1,200 tons of force. You get a ring with an outer diameter of 4 inches. Inner diameter, 3.1 inches. Height, 0.8 inches. Rings undergo heat treatment. Heated to 1,540 degrees. Held 30 minutes. Quenched in oil at 140 degrees. Cooling rate, 540 degrees per second. Tempered at 360 degrees for 2 hours. Hardness after heat treatment, 62 Rockwell. Then, grinding. The ring is clamped in a lathe chuck. The abrasive wheel spins at 100 feet per second. Removes a metal layer 0.004 inches thick per pass. Surface roughness, 0.08 millionths of an inch. That's 10 times smoother than glass. Deviation from roundness, no more than 0.08 thousandths of an inch. Balls are made by cold heading. Wire 1/2 inch in diameter is cut into 1/2 inch segments. Each segment is clamped between 2 dies. Pressure, 2 tons. The segment deforms into a sphere. You get a rough ball? It's ground between 2 cast iron discs. The discs rotate toward each other. Speed, 200 revolutions per minute. Between the discs, abrasive paste. Grit size, 40 micrometers. Grinding takes an hour. The ball shrinks by 0.012 inches. Final diameter, 0.46 inches. Deviation, plus or minus 0.004 hundredths of an inch. Sphericity, 0.08 thousandths. Roughness, 0.02 millionths of an inch. Bearing assembly. Inner ring, outer ring, 17 balls. Brass separator, lithium grease. Bearings done. It'll spin for 30 years, 1 billion revolutions.
Today we're at one of Europe's largest oil extraction plants, where ordinary sunflower seeds become the very same oil sitting in your kitchen. The facility sprawls across dozens of acres, silos towering overhead, pipelines everywhere, tanks as far as you can see. And hanging over everything, this warm, slightly oily air with a nutty undertone. You'd think it's simple, just squeeze and done. But when you see the scale of this operation, you realize between a seed from the field and that clear bottle on the store shelf, there's an entire chain of processes where temperatures hit 570 degrees Fahrenheit, pressure reaches hundreds of atmospheres, and raw material flows in at thousands of tons per day. Come on, let me show you how it all works. It all begins in the fall, when one grain truck after another rolls up to the plant from the fields. Each semi brings in 20 to 25 tons of sunflower seeds. At peak season, the plant receives up to 300 trucks a day. That's about 7,000 tons of raw material, every single day. But before a seed gets anywhere near production, it has to pass inspection. The lab at the entrance takes a sample from every truck with a long probe, stabbing into the grain pile at different depths. They check moisture, oil content, debris, and damaged seeds. Moisture can't exceed 7%, or the seeds will start rotting in storage. Good sunflower seeds have an oil content of 45 to 52%, meaning almost half the seed is pure oil. If the parameters check out, the truck heads to unloading. The seeds pour into underground hoppers, where elevators lift them into silos, massive concrete towers up to 130 feet tall, where the raw material is stored under controlled temperature and ventilation. From the silos, seeds move along conveyors into the prep area. First step, cleaning. Seeds pass through separators that remove rocks, twigs, stem fragments, and other junk that hitched a ride from the field. Magnetic traps pull out stray metal bits, bolts, wire scraps, anything that could wreck the equipment. After cleaning comes cracking. Special mills split the hull and free the kernel. Think of it like cracking sunflower seeds with your teeth, except at tens of tons per hour. The hull, that's the shell we spit out when we snack on seeds, here they don't toss it. Hulls get pressed into pellets and burned in the plant's boilers, generating heat and steam for production. The facility basically heats itself with its own waste. The clean kernels get crushed on roller mills. Heavy steel rollers flatten them into thin flakes about 12 thousandths of an inch thick. That's called conditioning. The thinner the flake, the easier it is to extract oil later. Surface area multiplies. The meats get sent to roasters, massive multi-tiered vats where they're heated with steam to 200 to 230 degrees Fahrenheit while constantly stirring. This process is called moist heat treatment. It softens the cell walls and lets the oil flow out more easily. The smell in this room is incredible. Thick, nutty, warm, makes you instantly hungry. From the roasters, the hot meats feed into screw presses, powerful machines that look like giant meat grinders. Inside, a steel auger spins, forcing the mass through a narrowing channel. Pressure builds to 4,400 to 5,000 psi, and the oil literally gets squeezed out of the meats, dripping through slots in the press housing into a catch tray. A hot golden stream pours continuously. It's mesmerizing to watch. This is pressed oil, dark, cloudy, with a strong roasted seed smell. Many people think this is the final product, but actually, the press only extracts about 60 to 65% of the oil. The rest hides in the cake, a dense compressed disc that comes out of the press hot and hard as wood. To grab the remaining oil, the cake gets sent to extraction, and this is where the real chemistry begins. The cake is crushed, flattened again into flakes, and loaded into an extractor, a long horizontal unit that looks like a slowly rotating carousel. Inside, the flakes get washed with a solvent, usually hexane, a volatile liquid that dissolves fats but doesn't mix with water. Hexane flows through the layer of cake, soaking up the oil, and comes out the other end as micella, a blend of solvent and oil. The process takes about an hour, and during that time, hexane pulls out virtually all the remaining oil from the cake. The fat content in the spent meal drops to 1%. Meal is what's left of the seed after the double pressing. It's protein-rich, up to 46%, and goes into livestock feed. Essentially, from a single seed, the plant gets oil for people, protein feed